Have you wondered what it's like to reach Mars? That red world we dream about, talk about, and treat like our next big home. But what if we might never actually see Mars the way we imagine? What if getting there is harder, riskier, and far more unforgiving than anyone wants to admit? Here's why the road to Mars might stay closed, no matter how badly we want to walk it. The quest for traces of life on Mars. If you really want to understand why we probably won't set foot there, you need to understand why scientists spend so much time searching for traces of life that might have existed billions of years ago. That question has shaped every rover, orbiter, lander, and every sleepless night inside mission control. And it's because the answer to that question tells us something uncomfortable. Mars is not what we hoped for. It never was. And it gets further from our reach every decade. Before scientists pointed robotic eyes and metal wheels at the planet, Mars lived mostly in the human imagination. It was never a quiet object in the sky. It was a story we kept rewriting. The ancient Egyptians tracked its wandering path. The Greeks named it after their god of war. And generations later, when telescopes finally grew sharp enough to see a little more than a red dot, Mars turned into a mystery that obsessed entire careers. In the late 1800s, Giovanni Schiaparelli adjusted his telescope in Milan and saw lines across the planet's surface. He drew what he thought he saw, long marks that looked like channels. In Italian, he called them canali. It simply meant grooves or channels. But the word didn't stay simple. It drifted into English and transformed into canals, which meant something very different. Canals suggested planning, intelligence, civilizations trying to survive on a dying world. Then came Percival Lowell in Arizona, a man who didn't just see canals, he mapped them. He drew them with purpose, crossing the Martian surface like highways built by an alien species working together to transport water from the poles down toward the equator. Scientists argued. Newspapers ran front-page stories. Telescopes across continents swung toward Mars. And for a moment, the world wondered whether we were staring at the final flickering days of a once great civilization. It sounds almost comical now, but in their defense, it was the first time humanity thought seriously about whether Mars had life. Not microbes, not bacteria, actual thinking beings. And that idea didn't fade away quickly. It grew into novels and radio dramas and science conferences where men in suits debated the ethics of contacting Martians. People forget that the original obsession with Mars wasn't about sending humans there. It was about who might already be living there. The truth started unraveling in 1965 when a blocky spacecraft called Mariner 4 swung past the planet and returned the first close-up photos ever taken of its surface. Scientists gathered around those images expecting to see something promising. Something like lakes or forests, or maybe even signs of the old canals that Lowell insisted were there. What they got instead was a desert so dead, so untouched, so violently empty that it silenced decades of imagination. No ruined cities, no canals, no water flowing across the ground, just craters, dust, and shadows. It was the moment the myth cracked. It was also the moment science began. Every mission since Mariner 4 has peeled back more layers of the planet, but each layer only seems to highlight another reason human biology doesn't belong there. It's not like researchers want negative results. Nobody spends their life building rovers that travel millions of kilometers just to confirm that a place is impossible. But Mars keeps doing exactly that. It keeps revealing another harsh surprise, another environment that stretches the limits of human survival thinner and thinner. When the Viking landers arrived in 1976, their main goal was straightforward. Touch down, analyze the soil, look for biological activity. The results were confusing at first. Some tests hinted at chemical reactions that looked almost biological. Others contradicted them. Even now, the Viking experiments are still debated, which tells you how complicated this question is. But what Viking confirmed without a doubt was that the Martian soil was not friendly. It wasn't neutral. It was chemically aggressive, filled with compounds that destroy organic molecules faster than scientists could test them. From that moment on, Mars wasn't seen as a cosmic neighbor. It was seen as a planet that wanted to erase evidence of anything ever living there. Rovers like Spirit and Opportunity later rolled across landscapes that looked beautifully barren from orbit, but were far more hostile up close. Curiosity arrived in 2012 and found radiation levels on the surface high enough to shred DNA. Perseverance landed in 2021 to search old riverbeds for traces of ancient life. But even in regions that once carried water, the surface is saturated with perchlorates, chemicals that disrupt breathing, attack human tissue, and make the dust dangerous to inhale. China's Tianwen-1 orbiter and rover added more data, not more comfort. Its measurements confirmed that solar wind slams into the planet with almost no resistance. Mars has no magnetic shield to deflect the radiation, and its atmosphere is barely thick enough to slow a falling feather. Each new mission keeps painting the same picture from different angles. Mars hasn't just lost the things that make a planet hospitable. It lost them in a way that makes getting them back almost impossible. What makes a planet habitable? When scientists talk about what makes a planet habitable, they don't speak in poetic lines or heroic metaphors. They use very specific requirements because life is not vague. It needs liquid water, not just ice or vapor. It needs a stable climate, not a world where temperatures can shift from a pleasant afternoon to deep freeze death within the same day. It needs an atmosphere thick enough to hold heat, block radiation, and prevent your lungs from collapsing the moment you take a breath. Earth checks these boxes almost too perfectly, which is why life exploded here. Mars checks none of them. Its atmosphere is thinner than anything that can support natural human breathing, even with pressure suits. Its temperatures drop to levels that break materials, not just fingers. Its radiation levels are high enough to cause cancer during the journey there, not decades afterward. Its soil contains compounds toxic enough to make farming a risky, chemically complicated challenge. Even the sunlight is a problem. Mars receives only a fraction of what Earth does. Solar panels degrade fast under Martian dust, and storms can shut them down for weeks. The idea of habitability isn't warm or vague. It's brutal math. And Mars keeps failing that math with every new measurement. The search for life on Mars continues today, not because scientists believe there are Martians hiding somewhere beneath the rocks, but because even the faintest trace of ancient life would reveal something massive. Mars was once warm, wet, and stable enough to support biology. And if it once had all of that, then losing it must have been catastrophic. Understanding how Mars died is a window into how fragile planets can be. The irony is that while scientists investigate whether ancient microbes once thrived there, they're also gathering a mountain of evidence showing why human beings probably never will. Every rock sample Perseverance drills, every chemical reading Curiosity takes, every atmospheric chart from orbiters, all of it points to a world that's not just unfriendly to humans, but actively dangerous. People often imagine Mars as a colder version of Earth, a dusty world you could fix with engineering. Just send enough machinery, build enough domes, melt enough ice. Terraforming, they call it. The kind of idea that sounds inspiring until you start reading the actual physics behind it. Because it turns out Mars isn't a fixer-upper planet. It's not an empty house that needs a little work. It's a building missing its foundation. The things Mars lacks aren't cosmetic. They're structural, the kind of things you can't replace even with unlimited technology. Mars doesn't have a magnetic field. That's not a minor detail. Without it, solar radiation strips away the atmosphere molecule by molecule. If you tried to rebuild the atmosphere, the sun would just tear it apart again. Mars doesn't have the right mass to hold a thick atmosphere in the first place, and it doesn't have the internal churn to generate a magnetic shield. These aren't problems you repair with machines. They're the result of a planet that cooled too fast and lost its inner energy long before humans existed. The more scientists learn about how the planet changed over billions of years, the more obvious it becomes that the Mars of today is not a place built for human lungs, human bones, or human cells. Yet the fascination persists. It always does. Maybe because Mars is close enough to tease us, but far enough to stay just out of reach. Maybe because we want a frontier that feels both dangerous and attainable. Maybe because the idea of another world gives people a sense of escape, a way to imagine something bigger than taxes and traffic and the noise of daily life. But enthusiasm doesn't change the physics. Optimism doesn't block cosmic rays. Ambition doesn't thicken an atmosphere. There's a line scientists repeat often when discussing Mars. They don't say it with sarcasm or frustration. They say it like a fact carved in stone. The obstacles to sending humans to Mars aren't theoretical. They aren't maybe problems. They're measurable, documented, quantified, tested, reviewed, reconfirmed. They're the kind of problems that don't care how much motivation you bring. They exist whether you believe in them or not. The difference between dreaming of Mars and actually reaching it is the difference between drawing a map and building a road. One is imagination. The other is construction, sweat, and physics you can't negotiate with. And the truth hits much harder when you look at the timeline of discoveries. Early astronomers dreamed of civilizations. Mariner 4 crushed that dream. Viking crushed the hope of living soil. Spirit and opportunity crushed the idea of a comfortable environment. Curiosity crushed the idea of safe radiation levels. Perseverance is now showing how fragile ancient Martian environments truly were, even during the planet's best days. Every mission debunked one more piece of the fantasy. It exposed a reality harsher than the last and confirmed something scientists didn't want to admit. The question isn't whether humans can survive on Mars someday. The question is whether Mars ever had a version of itself that could truly support life long enough to matter. And the answer, based on what we know, leans heavily toward no. Even if ancient rivers once carved through Martian valleys, even if lakes once filled its basins, the planet still dropped into a deep freeze so absolute that any life that might have existed had almost no chance of holding on. That's the kind of planet we're dealing with, a place that isn't just uninhabited, but unforgiving in every measurable way. And this shapes the central tension of modern Mars exploration. We're desperately searching for traces of life on a world that can't support ours. The more evidence we collect, the clearer the pattern becomes. Mars might have had a moment, brief, cosmic scale brief, where things lined up. Water flowed, temperatures held steady. The atmosphere had enough thickness to protect whatever tiny forms of life were beginning to emerge. But that window slammed shut early, and the conditions that followed weren't just harsh. They were fatal. The planet became dry, cold, irradiated, and chemically aggressive. A world that erases life faster than it can form. A world that sterilizes its own surface. And that's the planet people imagine we're going to colonize. The search for traces of life is still valuable. It teaches us how planets evolve, how climate collapses, how atmospheres break apart. It helps us understand the limits of biology in the universe. It gives us perspective on how rare Earth's stability actually is. Scientists aren't digging for fossils because they think Martian microbes will greet us when we land. They're digging because understanding the past tells us why the present is so inhospitable. But the biggest shock, the part audiences rarely hear, is this. The more we investigate Mars, the more obvious it becomes that our dream of going there is built on curiosity, not capability. Because capability requires physics, and physics has no interest in helping us. Mars is not a blank canvas. It's a planet with locked-in conditions that defy every tool we currently have. Its radiation levels don't shrink when we dream about exploration. Its atmosphere doesn't thicken out of respect for our ambition. Its dust doesn't become less toxic when we imagine greenhouses and domes. The planet stays exactly what it is: dry, frozen, unshielded, exposed, and chemically extreme. But how far is Mars really? The distance problem. There is a moment in almost every conversation about sending humans to Mars where someone says the distance is huge, but they say it lightly, the way people talk about a long drive or a faraway city. And the word distance ends up sounding smaller than it actually is. They might compare it to the moon, or call it a tough commute, or reduce it to a few numbers that seem manageable on paper. Yet once you break out of the casual way people talk about it and start dealing with actual measurements, orbital mechanics, transfer windows, and everything that happens to a fragile human body on a months-long journey through open space, the distance stops being a number and becomes the first great wall between humans and Mars. There is no shortcut to Mars, no straight-line highway stretched across a peaceful void, no simple acceleration followed by a gentle cruise, because the planets are not still, they are not waiting for us, and they are not positioned in a way that lets us come and go whenever we want. They move along their own paths, locked into gravitational moves controlled by the Sun. And that means any spacecraft trying to reach Mars must move according to those paths, not according to our schedules. This built-in orbital choreography turns distance into something that changes dramatically depending on the moment we decide to leave Earth. And this alone reshapes the entire mission before anything else is even discussed. Most people hear that Mars can be as close as 54.6 million kilometers and assume that is the trip, the whole story, the one number they need to keep in mind. But that number represents the absolute closest possible approach between Earth and Mars. An alignment so perfect that it almost never happens. And even when it does, spacecraft cannot fly straight across it, because everything in the solar system is moving at thousands of kilometers per hour. At the other extreme, when Earth and Mars sit on opposite sides of the Sun, the distance stretches to around 401 million kilometers, a separation so vast that it becomes almost pointless to think about sending anything during those months. This massive range creates a problem that appears simple but quickly becomes complicated. The distance is not fixed, which means the energy required, the travel duration, and the risk level change wildly depending on timing. A spacecraft heading for Mars has to aim for a point where Mars will be months in the future, not where it currently is, which forces mission planners into a narrow set of launch opportunities that exist whether we like them or not. Every time someone wonders why we cannot launch people to Mars anytime we want, the answer lies in this very specific orbital alignment that appears roughly every 26 months. These launch windows exist because spacecraft must follow what is called a Hohmann transfer orbit, a path that uses the least possible energy to travel between two orbits. It is not the fastest path, and not the straightest either, but it is the only one that makes the mission remotely realistic with current propulsion. To enter a Hohmann transfer orbit, the spacecraft must leave Earth at the exact moment when Mars will line up with the end of that elliptical path months later. Missing that window means missing Mars entirely, because the planet will have moved far ahead by the time the crew arrives at the point where the planet was supposed to be. You cannot catch up casually, and you cannot turn around easily, because every movement in space costs fuel, and fuel is mass, and mass dictates the entire architecture of the rocket. These windows are not flexible. They do not shift to accommodate delays, politics, budgets, weather, or unexpected technical problems. When the window opens, you go, and if you do not, you wait over 2 years for the next one. For robotic probes, this is inconvenient. For humans, this is a mission-shaping constraint that affects every design decision, every supply calculation, every emergency plan, and every conversation about how long astronauts must survive in a hostile environment far from Earth. The reality of 7 to 9 months in transit. Even if everything lines up perfectly and a spacecraft launches in the exact window that orbital mechanics allow, the journey itself becomes another enormous challenge. With current propulsion technologies, including chemical rockets and ion thrusters, the travel time sits somewhere between 7 and 9 months. That is the optimistic range, the kind of estimate that assumes no major detours, no unexpected loss of efficiency, and no complications that force the spacecraft to spend extra fuel adjusting its course. These months matter in ways people often overlook, because the human body did not evolve inside spacecraft drifting through radiation-filled space. On the International Space Station, astronauts are only a few hundred kilometers above Earth, still shielded by the planet's magnetic field. Yet even at that altitude, they face muscle loss, bone loss, fluid redistribution, and radiation exposure that require constant exercise and monitoring. A 7 to 9 month journey removes the protection of the magnetic shield entirely. exposes the crew to cosmic radiation and bursts from solar events, and isolates them in a tube where every gram is controlled. Every system must work flawlessly, and every failure becomes a direct threat to survival. The duration also influences the supplies the crew must carry. Food, water, oxygen regeneration systems, spare parts, medical equipment, exercise equipment, scientific instruments, communication systems, and radiation shielding all scale upward with time. The longer the mission lasts, the more mass the rocket must push off Earth, and every kilogram added to the spacecraft triggers a chain reaction that affects fuel requirements, launch vehicle design, and mission risk. People sometimes imagine that a spacecraft could travel faster by simply increasing thrust. But propulsion in space does not operate that way. You cannot burn enormous amounts of fuel continuously for months because carrying that fuel would require a rocket so massive that it collapses under its own weight. And even if that engineering barrier were solved, the cost would explode into levels no nation can sustain. Acceleration and deceleration each require fuel, and escaping Earth's gravity already consumes most of what rockets carry. The journey length is not just an inconvenience, it is a direct health risk. Outside Earth's magnetic shield, astronauts face a constant stream of cosmic rays, solar particles, and high-energy radiation that can penetrate most spacecraft materials. The longer the crew spends traveling, the higher the exposure climbs. NASA has already measured radiation levels on the way to Mars using detectors on robotic missions, and the results show that a round-trip surface mission would push astronauts close to, or even beyond, the lifetime exposure limits recommended for human health. Radiation causes cellular damage, increases cancer risk, accelerates aging, affects the central nervous system, and poses immediate danger during solar storms. A strong solar flare can deliver a lethal dose in hours, and current spacecraft shielding cannot fully stop this threat without becoming so heavy that the rocket becomes unflyable. Extended travel time turns radiation into a constant threat rather than an occasional hazard, as every additional week on the journey multiplies the risk. Some engineering teams have proposed lining the walls of the spacecraft with water or fuel to create an improvised shield. But the mass required to make a significant difference is so large that it becomes another obstacle to launch. How travel time strains supplies and mass. The extended duration of the journey forces mission planners into a tight corner when it comes to supplies. Food must last the entire outbound journey, the entire stay on Mars, and the entire return trip. Water must be recycled almost perfectly. Oxygen must be regenerated constantly. Every piece of equipment must be durable enough to survive years of operation without repair teams or replacement parts from Earth. Each of these needs adds mass. Mass increases the fuel required. Extra fuel increases the mass further. This cascading effect quickly grows beyond what any current rocket can handle. The cargo that must be transported includes not just essential life support, but redundancies for emergencies, specialized tools, radiation shelters, medical supplies, and hardware for landing, ascent, and surface operations. Unlike robotic missions, where failure means lost hardware, a human mission requires backups for backups because lives depend on them. This is why the distance to Mars cannot be treated casually. It shapes every kilogram, every subsystem, every contingency plan, and every timeline. The journey is not an afternoon commute across space. It is a slow, demanding process that traps astronauts inside a metal habitat for most of a year before they even reach the planet. To understand why distance becomes so destructive to mission architecture, you have to look at delta V, which is the measure of how much velocity change a spacecraft needs to complete a mission. Delta V is the currency of space travel, and it is brutally unforgiving. Reaching low Earth orbit requires a delta V of about 9.3 to 10 kilometers per second, depending on atmospheric and engineering factors. This is already an enormous challenge, and it is why rockets are gigantic multi-stage machines that burn through most of their fuel in minutes just to place a small fraction of their mass into orbit. But getting from low Earth orbit to a Mars transfer orbit requires several more kilometers per second of delta V. Then another chunk of delta V is needed for course corrections, velocity matching with Mars, and finally slowing down enough to enter its orbit or descend to the surface. After the stay on Mars is over, more delta V is required to launch from the Martian surface, escape its gravity, and begin the long journey back. Every meter per second of delta V demands fuel, and fuel adds mass, and added mass increases the delta V required. It becomes a loop that mission designers have to fight constantly. This is why rockets to low Earth orbit are massive, but carry payloads that look surprisingly small. Most of the rocket's body is fuel tanks, engines, and structure strong enough to support them. People often compare Mars missions to Apollo missions, but the Moon required only about 3 days of travel and far less delta V to reach. Apollo missions also relied on leaving most equipment in lunar orbit or on the surface. Even with those advantages, the Saturn V rocket was one of the largest and most powerful machines ever built, and it only delivered a small crew cabin to the lunar surface. Scaling that architecture to Mars would require rockets far beyond Saturn V in capability, and even then, the mass to delta V challenge makes the entire idea extremely difficult. How delta V shapes rocket mass. To understand the scale of the problem, consider this. Every kilogram added to a spacecraft forces engineers to increase the amount of propellant carried. Increasing propellant increases the total mass further. This compounding effect forces rockets into a vicious cycle where each addition to make the mission safer makes the vehicle heavier, which then requires even more fuel, which then increases the structural mass, and the cycle continues until the rocket becomes physically impossible to launch. This is not a theoretical model or an abstract engineering puzzle. It has already shaped every robotic mission to Mars. Those spacecraft are small and unmanned, yet each mission still requires massive launch vehicles just to place a relatively lightweight probe onto a trajectory that will meet Mars months later. When people imagine sending a full crew with food, water, radiation shielding, landers, habitats, ascent vehicles, and scientific equipment, they often underestimate how much mass this represents. Each of those items must be accelerated to escape velocity, then accelerated again to match orbits, then decelerated near Mars, and each step drains fuel that must be carried from Earth. The delta V budget dominates the design so completely that engineers cannot simply add more fuel to solve the problem. Adding fuel makes the spacecraft heavier, which increases the amount of fuel needed, and the spiral continues until it becomes unmanageable. The distance to Mars is not just a number on a chart. It is a barrier that interacts with every other challenge in Mars exploration. Radiation exposure becomes worse because the journey is long. Supply mass increases because the journey is long. Delta V increases because every extra kilogram must be transported over that long distance. Launch windows become inflexible because orbital mechanics demand a specific path with the lowest energy cost. Mission complexity grows because every subsystem must survive for years instead of days or weeks. Even communication delays become a factor. At closest approach, signals take several minutes to travel between Earth and Mars. At maximum separation, they take over 20 minutes. This delay prevents real-time problem solving, which means astronauts must solve many emergencies without immediate help from Earth. The distance isolates them physically and operationally, forcing mission designers to create systems that function autonomously, systems that must work without continuous support from ground teams. The distance shapes navigation, course correction, propulsion efficiency, and even the psychological stress of the mission. Human beings do not adapt easily to extended confinement, isolation, and the lack of immediate rescue. Unlike the International Space Station, which has a constant line of supply ships and the ability to return astronauts to Earth quickly, a Mars-bound crew becomes unreachable the moment they leave Earth orbit. No rescue craft exists. No backup exists. The distance makes sure of that. Some people argue that we could reduce travel times by using nuclear propulsion, high-efficiency ion drives, or advanced engines that do not exist yet. While future technologies might shorten the trip, the physics remain the same. You must still accelerate the spacecraft out of Earth orbit, still match the velocity of Mars, still carry enough propellant for slowing down, still survive the radiation environment, and still launch within the narrow transfer windows dictated by orbital mechanics. Even with better propulsion, you cannot eliminate the orbital geometry that determines where the planets are and how they move. Faster engines help, but they do not rewrite the layout of the solar system. The distance remains, and the mass problem remains, and the delta-V requirements remain. Until propulsion technology advances by orders of magnitude beyond anything currently available, distance will continue to dictate mission feasibility, mission safety, mission mass, mission duration, and mission cost. Because Mars is not close or convenient. Mars is not reachable in the way people imagine. It sits inside a moving solar system that forces every mission to play by rules written long before humans existed. And those rules turn distance into the first, largest, and most unyielding obstacle on the path to sending humans to the Red Planet. Radiation, the most unfixable barrier to Mars. Every era of Mars exploration has revealed a fresh obstacle, but none of those discoveries lands with the same punch as the radiation data. For decades, space agencies expected intense radiation on the trip to Mars. They understood that Mars had no magnetic field. They knew the atmosphere was thin. None of that came as a surprise. What did surprise them were the exact numbers recorded when real instruments crossed interplanetary space and touched down on the Martian surface. Those numbers were higher than expected, steadier than expected, and stubborn in a way that no engineering team has been able to shrink into something safe or manageable. The real turning point came from a small device strapped to the deck of NASA's Curiosity rover. When it launched in 2011, nobody outside the scientific community paid attention to it. It wasn't flashy. It collected no images. It didn't drill rock cores or fire lasers into boulders. It simply counted the invisible particles that would tear through a human body. That small tool, the Radiation Assessment Detector, RAD, changed every conversation about human travel to Mars the moment its data started streaming back. Curiosity was supposed to be a geology mission. Its main job was to inspect old sediments and tell scientists whether Mars could have supported microbial life. Yet every hour that RAD kept running, it sketched a different picture. It showed that the trip to Mars and the months spent on the planet would saturate astronauts with radiation doses that didn't just exceed current limits. They exceeded them by margins that satellites in Earth orbit rarely record even during solar storms. The more data scientists gathered, the more they realized the numbers weren't temporary spikes. They were the steady background reality of interplanetary space and of the Martian surface itself. The first reports did not spark public headlines the way a rover landing does. But within NASA and ESA, those findings hit harder than any broken wheel, failed antenna, or dust storm ever could. Space radiation isn't one thing. It's a mix of different types of particles, each with its own level of danger, and each almost impossible to escape once you leave Earth's protection. Curiosity's RAD readings confirmed that astronauts heading to Mars will be hit by two main categories of radiation: solar energetic particles and galactic cosmic rays. Solar energetic particles, or SEPs, come from eruptions on the Sun. Flares and coronal mass ejections push out charged particles that move fast and hit hard. Astronauts in Earth orbit can hide behind thick walls and wait for the storm to pass. Mission control can warn them in time. The International Space Station gets shielded by Earth's magnetic field. Crews are rarely in serious danger so long as they follow proper safety steps. But away from Earth, those same particles arrive with full force. A single strong solar event could deliver a radiation dose that crosses an astronaut's short-term safety limit in hours. These events don't happen every day, but the problem isn't their frequency. The problem is their unpredictability. Galactic cosmic rays, or GCRs, are even worse. They come from all over the galaxy. Supernovae and other violent cosmic events hurl atomic nuclei across space. These particles move so fast and carry so much energy that they punch through most materials. They smash atoms apart, create secondary radiation inside the body and damage DNA far more deeply than typical solar particles. The surface of Mars doesn't block them. The spaces between planets don't dilute them. Nothing in our current toolkit cancels them out without tremendous mass. Curiosity's RAD instrument measured the radiation dose during the entire trip from Earth to Mars. The spacecraft wasn't especially shielded. It wasn't built to protect humans, but the data is valuable because any realistic Mars ship will face almost the same conditions unless someone invents an entirely different propulsion or shielding system. RAD measured an average of 1.8 millisieverts of radiation per day during the cruise. That doesn't sound dramatic until it's compared with astronaut limits. A typical career radiation limit for NASA astronauts is set around 600 and 1200 millisieverts, depending on age and sex. The number exists because the risk of cancer increases sharply beyond that range. At 1.8 millisieverts per day, a standard 7-month Mars trip exposes the crew to around 378 millisieverts before they even land. If the trip stretches closer to 9 months, the exposure rises above 480 millisieverts, and that's only for the outbound journey. The return trip adds the same dose again. The surface of Mars adds more on top of it. Curiosity measured roughly 0.67 millisieverts per day on the ground. That's lower than interplanetary space, but still dozens of times higher than the average background radiation on Earth. A 1-year stay on Mars puts astronauts at around 244 millisieverts, added to the 400-500 millisieverts from the trip each way. By the time a crew leaves Mars and heads home, even before the return flight bombards them with another 400 plus millisieverts, they have exceeded the radiation career limits set for professional astronauts by a large margin. These numbers aren't theoretical. They come from real measurements taken over years. They don't soften with new data. Every new mission, InSight, Perseverance, Tianwen-1, adds more confirmation that the radiation environment around Mars doesn't fluctuate in a way that helps future astronauts. It stays consistently high. Why shielding fails at human scale? The simplest response to radiation is obvious. If you want to protect astronauts, you add shielding. The problem is that shielding in space isn't like shielding in a hospital or on the International Space Station. Space is full of particle energies that Earth-based materials handle poorly. And the moment a spacecraft tries to block cosmic rays with thick walls, another problem appears: mass. Every kilogram launched into space costs fuel, space, structural support, and money. Mars missions are already pressed against the limits of what rockets can lift. Adding shielding forces rockets to grow larger. And when rockets grow larger, they need more propellant, more structure, and more staging. Unlike SEPs, galactic cosmic rays cannot be blocked easily. Most materials don't stop them cleanly. Instead, they cause secondary cascades, showers of particles created when GCRs smash into shielding atoms. The more mass you add, the more secondary radiation you create. Some materials reduce the intensity better than others, but none eliminate it. NASA and ESA papers published in 2023 attempted to model how much shielding a Mars ship would need to bring the dose down to levels that fit inside astronaut safety limits. The answer wasn't encouraging. They calculated that the spacecraft walls would need to be thicknesses that no rocket could lift. Hydrogen-rich materials perform better, but the mass requirement still surpasses anything that can be launched in segments, assembled in orbit, or carried along without collapsing mission budgets and liftoff capacity. Even optimistic designs called for tens of tons of water or polyethylene surrounding a crew module like a heavy cocoon. But water is heavy. Polyethylene is heavy. Layering them thick enough to matter destroys the mass budget of any near-term Mars vehicle. Radiation shielding isn't solved with clever engineering. It's solved with mass. And mass is the one thing rockets hate more than anything. The engineering wall behind all of this is the classic rocket equation. Every kilogram of payload increases the fuel required. Every kilogram of fuel increases the structure required. Every kilogram of structure increases the fuel again. Mars missions already push rockets to the edge of their envelope because the delta V required to escape Earth, travel between planets, brake at Mars, land heavy equipment, launch again, and return is extreme. A spacecraft that can protect its crew against cosmic rays would weigh many times more than the current Mars mission designs. The launch mass would be so large that no existing rocket could carry even a fraction of it. Building multiple launches and assembling the vehicle in orbit increases complexity and creates a new set of engineering hurdles. Radiation shielding cannot be folded, compressed, or inflated. It must physically exist in place at full density the moment the ship launches. Every space agency faces the same math. Put a safe level of shielding around the astronauts, and the ship becomes too heavy to launch. Make the ship light enough to launch, and the shielding drops far below safe levels. That trade-off never narrows. Another proposal tries to bypass physical shielding by building an artificial magnetic field around the spacecraft. The vision sounds futuristic. Superconducting coils producing a field strong enough to bend incoming cosmic rays away from the crew compartment. It avoids heavy shielding and gives the spacecraft a bubble of protection similar to Earth's magnetosphere. The problem is that creating a magnetic field large and strong enough to stop GCRs requires energy levels far beyond current spacecraft power systems. Magnetic fields weaken with distance, so to create a bubble big enough to catch incoming high-energy particles, the coils must generate fields many times stronger than the strongest MRI machines on Earth. These coils must run continuously during the several-month cruise. They must survive faults without collapsing. They must operate with cryogenic temperatures for superconductivity. They must be lightweight, yet stable enough to support the immense magnetic forces pushing and pulling on the structure. They must not interfere with electronics or the crew's health. They must be assembled in space because they are too large to launch fully built. ESA and NASA studies show that magnetic shielding remains experimental. Even if someone built a small-scale version in orbit, it wouldn't be enough to protect a Mars crew. It might soften solar flare particles, but galactic cosmic rays would pass through the field the same way a bullet passes through fog. For magnetic shielding to help, the field strength has to increase beyond what today's materials can support. Without breakthroughs in superconductors, space-rated cryocoolers, and power generation, the system stays as a research concept. Some viewers imagine that once astronauts reach Mars, they can hide inside habitats that block radiation. The truth is that Mars gives almost no natural protection. The air pressure at the surface is about 0.6% of Earth's. That thin atmosphere barely slows incoming particles. Mars also lacks a global magnetic field. It used to have one billions of years ago, but it faded when the planet's interior cooled. Without a magnetosphere, cosmic rays and solar particles strike the atmosphere and surface directly. The only places where radiation levels drop meaningfully are deep underground or beneath meters of soil or rock. Habitats buried that deeply require excavation machines heavier than any robot sent to Mars so far. Building them would take time, energy, and a large crew, none of which can practically reach the planet until the radiation problem is solved. Even inside a surface habitat with moderate shielding, RAD's numbers show astronauts still receive doses far above Earth standards. The Martian atmosphere adds only a small buffer. Dust storms do not help. Clouds do not help. The thin sky is almost transparent to radiation that comes from distant supernovae. Mars is like a planet with its roof missing. Time makes radiation worse, not better. The longer a mission lasts, the more radiation adds up. This makes Mars very different from the Moon. A lunar mission lasts days or weeks. A Mars mission, at minimum, lasts 2 to 3 years because of the transfer windows. Crews can't leave early and come home whenever they like. They have to wait for the planets to realign. During that waiting period, astronauts live under steady exposure, with occasional spikes from solar activity and constant bombardment from cosmic rays. Every extra month added to the surface adds another chunk of dose. Every extra day, the return flight is delayed, adds more. Radiation is cumulative, and cosmic rays do not take breaks. Human biology can repair DNA damage but not this much. When cells cannot keep up with repairs, mutations accumulate. Some lead to cancer, others harm bone marrow, lung tissue, the circulatory system, or the central nervous system. Radiation also affects the immune system, making astronauts more vulnerable to illness during missions far from medical help. These effects aren't speculation. They are measured in animal studies, in long-term data from astronauts, and in decades of radiation biology research. Astronauts on the ISS already push close to their career limits despite Earth's magnetosphere blocking most cosmic rays. A Mars crew would face far higher doses for far longer periods. Cosmic ray intensity rises and falls with the Sun's activity cycle. During solar minimum, when the Sun is quiet, cosmic rays flood the inner solar system more strongly because there is less solar wind to push them away. During solar maximum, galactic cosmic rays decrease, but dangerous solar eruptions become more common. This creates a problematic choice: travel during solar minimum, and the crew faces the highest GCR levels ever measured, the kind RAD recorded. Travel during solar maximum, and the risk of deadly solar storms increases. There is no good time to send a crew under current technology. Choosing a safer period only means accepting a different flavor of danger. Some suggest using faster propulsion to cut the crew's time. Nuclear thermal rockets or nuclear electric propulsion could shorten the journey, but not enough to shrink radiation from years to something tolerable. Even if a ship could reach Mars in 3 months, which is optimistic, that still equals around 162 millisieverts for the outbound trip at the radiation levels RAD measured. With the stay on Mars and the return trip included, astronauts still exceed modern career limits. To go low enough, trip times would need to shrink to weeks. That demands propulsion systems far beyond current nuclear concepts. It requires technologies that don't exist in labs and may require physics breakthroughs, not simply engineering advances. Changing the distance isn't an option either. Mars does not move closer. Transfer windows do not become more frequent. Mission duration cannot compress itself to avoid the problem. Building habitats underground could reduce surface radiation dramatically, but it creates new challenges. Excavation machinery must be delivered to Mars, and those machines must be able to operate for months in extreme temperatures, dust, and reduced gravity. No rover or lander in Mars history has carried anything close to the mass required to dig large tunnels or caverns. Even if such machines landed successfully, they need power. Solar panels get covered in dust. Nuclear power sources must be shielded from the crew. Large-scale excavation changes the entire blueprint of Mars settlement. Instead of building simple habitats, crews must become miners, engineers, geological experts, and construction workers in an environment that punishes every mistake. And until those underground shelters are built, astronauts must live on the surface, absorbing radiation at rates that break through their lifetime limits in a single mission cycle. Why Mars's soil isn't a magic shield. Some propose covering surface habitats with Martian soil. Regolith can block a portion of incoming radiation, but only when layered thick enough to matter. Models suggest 2 to 5 meters of regolith might bring cosmic radiation to safer levels. Collecting that much soil requires industrial equipment, not hand tools. Rovers can scoop dust and small pebbles, but that doesn't compare to the volume needed to bury a habitat. The soil also clings electrostatically, contains perchlorates that complicate handling, and shifts under low gravity. The moment a habitat is covered by regolith, its structure must support the load. Lightweight modules designed for launch aren't built to carry tons of soil on top. Shielding from soil is possible in theory, but only after crews survive long enough to build the system. And that initial period remains the unsolved part. Every time a new radiation study comes out, the numbers shift slightly, but the message stays the same. Space between Earth and Mars is filled with GCRs that our species has never evolved to withstand. Mars offers almost no protection. Shielding requires mass that rockets cannot lift. Magnetic shielding requires power and materials that do not exist yet. Faster trips require propulsion that remains decades or physics breakthroughs away. ESA's 2023 study modeled multiple shielding combinations. NASA's radiation teams cross-checked them with Curiosity data, ISS medical records, and simulations of long-term exposure. They found that even an optimistic Mars mission design still pushes astronauts above their career limits, and that the only way to stay within those limits is to shorten the mission drastically, add extraordinary shielding, or accept a higher cancer risk. Shortening the mission isn't possible. Adding shielding breaks launch capacity. Increasing cancer risk is not acceptable because it's not just cancer. The dose levels affect organs, immune systems, brain tissue, and long-term cognitive performance. The more advanced the models become, the clearer the radiation problem looks. It does not bend. It does not fall into place when technology improves slightly. It stands as the one factor that refuses to shrink with better rockets, better planning, or better training. Every serious Mars mission proposal from the last 20 years confronts the same page of data. It lists radiation levels measured by Curiosity, by MAVEN, by Odyssey, by the ISS dosimeters, by detectors on probes passing through deep space. Those instruments do not disagree. They confirm the same truth over and over. Space beyond Earth's magnetic field is hostile at a constant rate that surpasses safe limits for long-term missions. It's the one part of a Mars mission that cannot be redesigned easily. Engines can improve, food systems can be upgraded, habitats can be scaled up. But radiation is not a design problem. It is a cosmic environment problem. It is the signature of a solar system that isn't built for human bodies. Every other barrier to Mars, distance, landing, fuel, life support, can be met with engineering. Radiation remains the one barrier that needs breakthroughs, not incremental progress. It sits untouched, unsoftened, and unmoved by decades of research. And it is the reason every Mars timeline slides backward the moment scientists run the numbers honestly. The human body isn't built for 0.38 G. Every modern astronaut who returns from the International Space Station brings back a clear look at what happens to a human body when gravity disappears. It doesn't take long. Muscles thin, bones weaken, fluids rush toward the head. Even astronauts who train daily with strict routines step off the landing capsule with bodies that feel unfamiliar. That's after 6 months in microgravity, inside a controlled environment, with world-class medical support waiting on the ground. Those ISS missions gave scientists decades of data. They mapped out how fast muscle fibers shrink, how bone density drops each month, how the heart slowly changes shape, and how the immune system reacts when the body no longer has a constant pull downward. But everything measured in orbit was gathered under perfect microgravity, not under Mars gravity. And that is the part that still stands as a blank page. Mars gravity is roughly 0.38 G. It's not zero, it's not Earth. It's a middle zone that no human has ever lived in. The body has no evolutionary experience with it. The ISS has given clues about what happens when gravity disappears completely. And those clues suggest that even a partial gravity environment creates long-term conditions the body may struggle with in ways scientists cannot fully predict. What is known is that the changes seen on the ISS pose serious risks during a 2 or 3 year mission. Even with exercise equipment, even with constant monitoring, even with perfect discipline. Astronauts living on the ISS work out about 2 hours a day, every day, using devices built to simulate running, weightlifting, and cycling. Despite this, muscle loss continues steadily. Studies show the human body in microgravity loses roughly 20% of muscle mass in key groups during a long mission, unless aggressive countermeasures are used. Even with those countermeasures, loss still occurs. The legs weaken first because they no longer support the body's weight. The back muscles follow. The hips lose strength. The stabilizing muscles that hold the spine upright shrink quickly. Over time, the entire lower half of the body begins to reshape itself around a lifestyle where standing is no longer required. Mars gravity won't reverse those changes. It's strong enough to stress the body, but too weak to keep muscle at Earth levels. That means a Mars crew will suffer some version of the same decline, but stretched over years instead of months. The biggest issue is that the ISS crew spends most of their mission inside a safe and stable cabin where small injuries are manageable. Mars crews will have to stand, climb, lift equipment, carry tools, and work in suits that restrict movement. Doing that while muscle strength falls each month introduces day-to-day risk that can't be managed the same way as on the ISS. A simple misstep on Mars, like losing balance on uneven ground, becomes far more serious when the body has lost the strength to correct it. Bones respond to gravity. On Earth, each step pushes calcium into bone structures, keeping them dense and strong. Microgravity removes that force. Astronauts on the ISS lose 1 to 1.5% of bone density per month in their hips and spine. These aren't tiny losses. They resemble the same rate seen in elderly patients with osteoporosis. This bone loss does not immediately stop when astronauts return to Earth. It can take years to restore density, and some never regain the full strength they had before launch. Now imagine this process during a Mars mission. Astronauts will spend months in microgravity during the trip, then land in 0.38 G, where bone-building forces are weaker than Earth. After spending over a year there, they must launch from Mars, re-enter microgravity on the return trip, and then face Earth gravity again, with bones weakened for years. A broken bone on Mars is not like breaking a bone on Earth. There is no hospital, no orthopedic surgeon, no fast evacuation. Bone demineralization increases this risk significantly. A slip on a ladder, a twist on uneven terrain, or a fall during extravehicular activity could produce injuries that compromise the entire mission. ISS countermeasures can delay bone loss but cannot stop it, and none of those solutions were designed for multi-year missions. The longer the exposure, the harder it is for the skeleton to recover, and the more dangerous every physical task becomes. How fluids shift through the body. When gravity weakens, fluids move upward. On the ISS, astronauts wake up with puffy faces and thinner legs. Over time, this pressure increase around the head creates problems that go beyond discomfort. The central issue is a condition known as spaceflight-associated neuroocular syndrome, or SANS. Some astronauts develop swelling around the optic nerve. Their vision changes. The shape of their eyes shifts slightly as pressure increases. Missions have documented cases of farsightedness that linger long after landing. If this happens after months in microgravity, the concern becomes much larger during Mars missions, where the total time away from Earth stretches to 2 or 3 years. Partial gravity has not been tested on humans, so nobody knows whether fluids continue shifting in the same way or whether the effect changes. What is known is that SANS does not require zero gravity to appear. Any reduction in gravity disrupts how fluids circulate. If the crew's eyesight changes during the mission, the consequences affect navigation, surface operations, control panels, and daily tasks that require precision. On a planet with dust storms, rocks, and equipment hazards, reduced vision is not a minor inconvenience. It directly impacts survival. The ISS is a laboratory. It rotates crew members every 6 months. It provides constant medical oversight. If a problem develops, astronauts can return to Earth within hours. Nothing about that setup applies to a Mars mission. The ISS exercise machines weigh hundreds of kilograms and require constant maintenance. They depend on a stable power supply and controlled environment. Even with that support, the machines don't fully prevent muscle or bone loss. Mars missions cannot carry equipment that large. Every kilogram counts. That means exercise hardware designed for Mars must be lighter, smaller, and more compact. And smaller equipment equals reduced effectiveness. The ISS also uses dietary plans tailored for microgravity. Fresh deliveries arrive several times per year. Mars missions will rely on stored food for long stretches. Nutrition degrades over time. Vitamins lose potency. Minerals break down. Food transported for a 3-year mission will not maintain the same quality throughout the journey. That directly impacts how the body repairs bone and muscle. ISS astronauts undergo medical checks using advanced diagnostic tools. Mars crews will not have those systems. They will not have bone scanners. They will not have full imaging suites. They will have limited medication, limited equipment, and no backup crew floating a few hundred kilometers overhead. The ISS environment is forgiving. Mars isn't. Once a Mars crew member reaches a critical level of bone or muscle loss, there is no emergency return path. Heart remodeling and circulation challenges. Space agencies have measured how the heart reacts to microgravity. When a body no longer needs to fight against gravity to push blood upward, the heart begins to shrink. The left ventricle decreases in size, cardiac output changes. Over time, the heart adapts to the new environment, but that adaptation creates problems when crews return to Earth. Some astronauts faint when they stand for the first time after landing. Others develop orthostatic intolerance, an inability to regulate blood pressure when moving from lying down to standing. Mars gravity sits between Earth and microgravity. It's strong enough to demand effort, but too weak to keep the heart fully conditioned. That middle zone may push the cardiovascular system into a stressful cycle. Too much unloading to stay strong, too much loading to stay relaxed. Scientists have models, but no human has ever tried to live that way long enough to know what happens. If the heart continues to remodel in 0.38 G, even minor physical tasks can become exhausting. Climbing steps inside a habitat, carrying tools across the surface, lifting a sample container, all take more out of a weakened heart than predicted. Over months and years, this strain could limit surface activities and reduce the crew's ability to perform essential tasks. This is not a temporary discomfort. The risks involve long-term heart health during a mission with no medical evacuation options. Science has already shown how fragile human vision becomes in altered gravity. Some astronauts have returned with permanent changes. That is, after half a year. Mars crews face multi-year missions. If pressure on the optic nerve continues to rise in partial gravity, or if fluid shifts accumulate faster than expected, vision impairment becomes a constant issue. It affects reading instruments, using tools, operating machinery, and identifying hazards during extravehicular activities. The helmets on Mars suits are rigid. Limited field of view is already part of the design. Add vision changes and tasks that demand sharp clarity, like connecting cables, spotting cracks on equipment, searching for safe ground, become harder. SANS also affects the shape of the eye. Long exposure could force astronauts to rely on corrective lenses they didn't need before launch. If those lenses are damaged, contaminated, or misplaced, eyesight problems cannot be corrected easily. Mars dust finds everything. Equipment gets scratched, supplies wear down. Vision is not optional for surface missions. It's central to every movement. Spaceflight alters the immune system. Studies show astronauts become more vulnerable to infections during and after missions. Latent viruses in their bodies can reactivate. Cuts and wounds heal more slowly. Stress hormones increase as the immune system shifts into a different mode. On the ISS, these problems are manageable. Astronauts operate in a sterile environment with regular cleaning schedules and strict hygiene rules. But Mars has dust that contains perchlorates. It has abrasive particles that can irritate lungs and skin. It has close quarters habitats where any illness spreads quickly. A suppressed immune system in a Mars environment increases risks of respiratory issues, skin infections, and delayed healing after minor injuries. A simple cut that would heal in days on Earth may linger for weeks on Mars. That slows down surface work and puts the whole crew at risk. These immune system changes are not mild side effects. They shape how well astronauts can adapt to the demands of a hostile planet. The Mars suit problem. Surface suits designed for Mars must balance mobility, pressure, insulation, and dust protection. They are heavier and bulkier than clothing worn on the ISS. Astronauts walking in 0.38 G still feel the suit's mass. That mass demands strength. It demands stamina. It demands joints and muscles that can support repetitive motion. But those muscles are already weakened from the months of microgravity during the trip. The heart is weaker. The bones are thinner. The balance system is less reliable. A Mars suit that weighs 45-50 kilograms on Earth still weighs around 17–19 kilograms on Mars. That is a noticeable load for astronauts whose bodies have lost strength. Walking across a flat surface becomes taxing. Climbing slopes becomes difficult. Recovering from a stumble becomes dangerous. Mars suits also introduce pressure differences that the body must adapt to. Hand strength decreases during missions, making it harder to grip tools through gloves. Repeated strain increases fatigue. This combination of weakened muscles, reduced stamina, and suit constraints creates a constant physical challenge that no training on Earth can fully prepare astronauts for. The most important fact in this entire discussion is simple. Not a single human has ever lived in partial gravity long enough to measure the effects. The moon missions lasted a few days. Astronauts never adapted to lunar gravity because they didn't stay long enough. All long-duration missions have been done in microgravity. Scientists can model the effects. They can gather data from rodents in centrifuges. They can simulate weight changes with bed rest studies. But none of these methods accurately represents living, working, sleeping, and performing complex tasks in 0.38 G for years. This means Mars crews are entering an environment where doctors cannot predict full medical outcomes. The body may develop issues that do not appear in microgravity or on Earth. Muscle groups may weaken in unexpected patterns. Bones may lose density at unfamiliar rates. Vision may shift faster or slower than predicted. Without human test data, every Mars mission plan is built on assumptions. Some of those assumptions rely on best-case scenarios. For a planet as hostile as Mars, best-case planning is a serious risk. The idea of artificial gravity shows up in almost every conversation about long-term space travel. The concept is straightforward. Spin part of the spacecraft to create centrifugal force. That force mimics gravity. But the engineering reality is difficult. To create even a fraction of Earth gravity, a spacecraft must rotate at a specific rate. If the radius of the rotating section is small, the spin rate must be high. High spin rates cause nausea and disorientation. The inner ear struggles to adjust. Astronauts become dizzy and unable to perform tasks. To reduce spin rate, the radius must increase. That means building structures dozens of meters across. Those structures add mass. They need reinforcement. They need bearings, joints, and systems that can operate for years without failing. They must survive launch stresses, vacuum conditions, micrometeoroids, and thermal extremes. No spacecraft has ever been built with a rotating crew section. No test platform exists in orbit. No one knows how long such a system could run before breaking down. Even if the system works, the transition between microgravity and artificial gravity becomes another biological challenge. The body has to adjust repeatedly as the crew moves between sections. On a Mars mission, if artificial gravity fails mid-flight, the crew loses the very system designed to protect their health. Repairing a massive rotating structure in deep space is far beyond current capabilities. Artificial gravity looks clean on paper, but becomes one of the heaviest, most complex, and most failure-prone systems ever added to a spacecraft. Centrifugal gradients complicate everything. Even if a rotating crew section is built, gravitational force is not uniform inside it. The floor experiences the strongest pull, the head experiences less. That gradient alters how blood moves, how muscles behave, and how balance systems function. Daily life inside such an environment would feel unfamiliar. Simple movements require relearning. Fluids may still collect in the upper body. The body may adapt partially, but not fully. Some muscle groups strengthen while others weaken. No long-term data exists for how these gradients affect the body. Engineers and doctors cannot say with certainty whether artificial gravity systems protect bone density, stabilize vision, or support heart function in the way Mars missions need. Without answers, artificial gravity remains a concept that solves one problem while possibly creating another. The biggest challenge with artificial gravity is mass. A rotating structure that can support a crew for years is heavy. The bearings alone weigh hundreds of kilograms. Reinforcement adds more. Power systems, control systems, stabilization, and safety mechanisms add more. Mars missions already push rockets to their limit. Adding tens of tons of rotating structures breaks every mass estimate. Launch vehicles would need upgrades beyond current capabilities. As mass increases, fuel requirements increase. As fuel requirements increase, structural mass increases again. The entire mission architecture expands until it becomes unmanageable. There is a reason no space agency has put a rotating habitat into orbit. The mass penalty is enormous. The ISS, the largest structure humans have assembled in space, has no artificial gravity section because the added mass and complexity outweighed the benefits. A Mars mission is far more demanding than the ISS. If the ISS cannot carry artificial gravity, a deep space vehicle is even less likely to support it. Without artificial gravity and without reliable countermeasures, astronauts face multiple years of biological strain. Muscle loss continues, bone density falls, the heart shrinks, vision changes, the immune system weakens, balance and coordination decline. These issues don't stay isolated, they compound each other. A weakened skeleton paired with weakened muscles increases risk of fractures. Reduced vision paired with lower balance awareness increases risk of falls. A stressed heart paired with heavy suit operations limits surface mobility. A compromised immune system paired with Mars dust creates hazards from minor infections. Mars crews cannot avoid physical labor. They must carry equipment, build habitats, maintain life support systems, and move across rocky terrain. Every part of that work requires a body strong enough to adapt. But the body in 0.38 g may be too weak to keep up. Every attempt to reach Mars begins with a simple question that becomes complicated the moment engineers pull out actual numbers. How do you lift enough mass off Earth to support a human trip that lasts years? The real cost of lifting anything off Earth. This is where the dream starts to bend under physics that doesn't care about excitement or ambition. Because every extra kilogram you try to push upward demands more fuel, and that extra fuel adds mass, which needs even more fuel, and that fuel adds even more mass. This loop doesn't stop. It keeps stacking until the rocket grows into a tower built out of nothing but the fuel needed to lift the fuel needed to lift the fuel. Mars isn't a place you visit with a small supply crate and a brave smile. A crew needs water, oxygen, food, tools, spare parts, radiation shielding, fuel for course corrections, fuel for Mars orbit insertion, fuel for Mars landing support, fuel for leaving Mars, and fuel for returning home. All of that mass must be pushed through Earth's gravity well before the adventure even begins. When engineers run the numbers, the picture doesn't soften. A Mars transfer vehicle large enough to keep humans alive for months, and then bring them home again, carries tens of tons of equipment and support material. Even the most optimistic mission outlines from major space agencies show total mission masses climbing into the hundreds of tons. Then you see the actual breakdown of propellant required just to push a large spacecraft into orbit. You discover that launching pieces separately doesn't make the physics easier. It only spreads the difficulty across multiple rockets. That's why Mars mission diagrams look like complex rearrangements of fuel tanks, habitation modules, propulsion stages, heat shields, and cargo bays being built in Earth. Orbit like a giant puzzle, you assemble one stressful step at a time. This is the shadow that hangs over every bold Mars proclamation. Rockets can lift heavy loads, but the moment you scale up to what a sustainable human mission actually requires, the numbers push back hard. The hard boundary behind all this is a century-old equation that refuses to be ignored. The Tsiolkovsky rocket equation states that the velocity you can reach depends on how much fuel you carry and how efficiently the engines use it. The result is brutally straightforward. To reach higher speeds, you need a higher fuel fraction. But rockets have a limit. You can't strap infinite propellant to them because the rocket must also lift its own tanks, structure, engines, and payload. To get a spacecraft from Earth's surface to low Earth orbit already consumes the majority of the rocket's total mass. Only a tiny percentage ends up as usable payload, and that's just for orbit. Mars needs far more velocity than orbit. You have to escape Earth completely and shape a trajectory that will intersect a planet that is moving at tens of kilometers per second around the Sun. The rocket equation doesn't care how much humanity wants Mars. It doesn't care how inspiring it sounds when someone says we should be a multi-planet species. The math stays the same. The larger the mission, the tighter the noose. And crewed Mars missions are enormous. When people imagine a spacecraft going to Mars, they often picture something sleek and futuristic. The actual engineering drawings look more like industrial scaffolding, fuel tanks welded in clusters, protective shells taped around fragile parts, and long tubes holding equipment that needs to function without rest for years. Nothing about it is light. Nothing about it is simple. Nothing about it behaves like the clean science fiction image that fuels the hype. Why chemical rockets hit a wall first? Chemical rockets, whether kerosene, methane, or hydrogen, are incredible machines, but they exist near their physical limits. The efficiency you get out of a chemical reaction is capped by the energy released per mole of fuel. Liquid hydrogen and liquid oxygen give the highest specific impulse among standard propellants. But even that isn't enough to make crewed Mars missions practical at full scale. You can push a small robotic lander to Mars with chemical propulsion because robots don't need radiators the size of billboards, food freezers, life support recyclers, pressurized cabins, exercise machines, medical stations, spare filters, and all the mass of the infrastructure that keeps organs working and bones intact. A robot mission is a backpack. A human mission is a moving house, so chemical propulsion reaches its limit early. You can burn more fuel, but the equation punishes that choice by demanding even more fuel to lift the added fuel, and then even more fuel to lift that. You get trapped. And this is before you think about the return trip. If you bring the fuel for the journey home from Earth, the mass skyrockets to impossible numbers. If you try to make the fuel on Mars, you now need factories, feedstock, giant energy systems, and months of operation before the crew even arrives. And those machines themselves must be landed on Mars safely. An engineering task that alone pushes into one of the hardest landing operations ever attempted. Chemical rockets remain the default because they're the only option we have that's fully tested. But they don't match the scale of what a human Mars mission demands. The physics never relents. Nuclear thermal rockets sound like the game changer everyone is waiting for. The idea is simple. Use a nuclear reactor to heat hydrogen to extreme temperatures, then push it out a nozzle to get much higher efficiency than chemical rockets can offer. In principle, this boosts the specific impulse enough to cut travel time and reduce the mass required for fuel. Engineering reality is less generous. A nuclear thermal engine requires materials that can withstand temperatures above 2,500 degrees Celsius while remaining stable under intense neutron bombardment. It needs shielding so the radiation from the reactor doesn't fry the crew. But shielding is heavy, and the more shielding you add, the less payload you can carry. But if you reduce shielding, the crew is exposed to lethal doses. There's also the political side. Launching a nuclear reactor on top of a rocket filled with explosive propellants has to pass strict safety rules. A failure during ascent could scatter radioactive material across vast areas. And the biggest problem is that nuclear thermal propulsion still isn't flight-ready. Tests done in the 1960s proved it was possible, but those engines never flew. Modern development programs encountered materials problems, cost issues, and stalled funding. The gap between laboratory demonstrations and a full, human-rated nuclear propulsion system remains huge. So nuclear propulsion stays stuck in the phase where it looks attractive on paper, but refuses to become hardware that can carry a real crew across the solar system. And without that upgrade, we return to chemical rockets and their unforgiving limits. Even if you somehow lift the mass into orbit and assemble a Mars transfer vehicle, the engineering grind doesn't get easier. A Mars ship must run non-stop for months, with no resupply, no emergency service dock, and no way to power down for repairs. Every pump, valve, wire, sensor, and filter must hold under conditions no Earth facility can replicate for that long. The ship takes micrometeoroid hits. It sees intense cosmic radiation. It endures thermal swings that can stress metals until hairline cracks appear in the wrong place. Each defect becomes a threat that can cascade. A stuck valve can starve the engines. A damaged radiator can overheat electronics. A failed sensor can hide a larger problem. Earth orbit lets you fix mistakes. Deep space punishes every oversight. The mass problem returns here as well. Redundancy means safety, but redundancy means more equipment, which means more mass, which requires more fuel. Every piece of backup hardware adds weight, so engineers must decide what to sacrifice. Life support reliability suffers first, comfort suffers next, safety margins shrink. The fight against heat and cold. A spacecraft near Earth deals with fairly moderate thermal conditions. The sun warms one side, space cools the other, and engineers design insulation and radiators that keep the cabin at safe temperatures. Deep space strips away those comforts. As the ship moves toward Mars, it leaves Earth's thermal environment and enters long stretches where sunlight weakens and cabin temperatures drop unless heaters run constantly. Heaters use power, and power systems add mass, and again the fuel equation tightens. When the ship swings closer to the sun during parts of its orbit, components heat up fast. Surfaces expand and contract repeatedly over months. That cycle alone can fatigue materials. Thermal control isn't a background detail. It shapes the entire design of a Mars craft. You need radiators wide enough to bleed heat from electronics, but those radiators are fragile and must survive micrometeoroid strikes. You need insulation that protects against cold without trapping too much heat. You need pumps that push coolant through miles of tubing with perfect consistency. Each of these systems must operate without downtime. Each adds mass. Each reminds engineers that the list of necessary hardware grows faster than the list of hardware you can actually launch. If the ship reaches Mars and the crew completes their mission and somehow refuels for the trip home, another major engineering fight begins, surviving the descent back through Earth's atmosphere. Returning from Mars isn't like returning from the ISS. The spacecraft approaches Earth at far higher velocity, over 11 kms, because it must fall from interplanetary speeds, not low Earth orbit speeds. That difference creates a heat load so intense that current crew-rated heat shields don't match what the spacecraft would endure. A heat shield large enough and strong enough to survive that slam into atmosphere stretches engineering to extremes. Materials must withstand blistering temperatures. The shield must not crack. It must stay attached under huge aerodynamic forces. It must protect a cabin full of fragile equipment and human organs weakened from months in reduced gravity. When scientists calculate how much heat must be absorbed or deflected, they end up with heat shield concepts that are thicker, heavier, and more complex than anything flown before. And again, mass grows. And the rocket equation punishes that growth. Even if you solved every issue of mass, heat, and propulsion, the mission still runs into a wall that isn't physical. It's the speed of light. Mars isn't far enough for signals to vanish, but it's far enough to cause delays that reshape how the crew operates. The gap between Earth and Mars varies, but during most of the mission, the time delay ranges from about 4 to 24 minutes one way. This means you cannot rely on fast decisions from mission control. You cannot get instant support during emergencies. You cannot troubleshoot in real time. If something breaks, the crew must solve it on their own with whatever tools they brought. If a fire starts, they can't ask for evacuation procedures. If a component fails during landing or takeoff, Earth can't guide them through backup sequences. If the ship experiences a pressure leak, there is no direct lifeline. This delay changes the design of the spacecraft. You need onboard diagnostics. You need autonomous decision systems. You need equipment that can identify failures and reroute power or switch modes without waiting for human approval. You need computers that can correct navigation without input. All of those systems add more hardware, more mass, more power demand, more potential failure modes. And once again, the mission architecture grows heavier and harder to launch. A crewed Mars mission stretches spacecraft engineering in every direction at once. Mass wants to go up, fuel wants to go up, heat shield size wants to go up, radiation shielding wants to go up, life support wants to go up, redundancy wants to go up, propulsion complexity wants to go up, communication autonomy wants to go up, launch capacity stays the same. This mismatch isn't abstract. It's not a small gap that clever engineers overlook and later solve. It's the central problem that blocks every realistic crewed Mars mission plan. Engineers adjust one variable and another swings out of control. Reduce mass and you cut safety. Increase mass and the rocket equation shuts you down. Shrink redundancy and a single failure can end the mission. Add redundancy and the fuel requirement becomes unmanageable. Shrink shielding and the crew receives a radiation dose that breaks medical limits. Add shielding and the ship becomes too heavy to launch. The entire design becomes a tightrope stretched across physics that never stop pulling downward. Space agencies know this. That's why internal documents are cautious even when public messaging sounds confident. The engineering teams who run mass budgets and propulsion simulations see the full picture. They know how many tons of equipment are required to keep humans alive in deep space. They know what happens when you scale up life support systems. They know how much propellant must be lifted to make the return trip possible. Chemical propulsion struggles. Nuclear propulsion remains stuck. Thermal systems strain. Heat shields balloon in size. Communication delays complicate operations. Every kilogram threatens the entire mission architecture. This is what makes spacecraft engineering one of the largest obstacles in the entire Mars dream. Not because engineers lack vision, but because physics stays the same no matter how inspiring the mission sounds. The fragile system, keeping humans breathing. A human trip to Mars only looks bold from the outside. From the engineering side, the entire mission depends on one thing that refuses to cooperate with long timelines: a closed life support loop. A ship heading toward Mars has to recycle water, remove carbon dioxide, generate oxygen, and keep that cycle stable for years without outside help. This is the point where Mars missions turn from daring to dangerous, because every part of that loop has already shown how fragile it is during short missions in low Earth orbit. The International Space Station is the reason we know this. The ISS isn't a testbed for ideas. It's a real environment where life support systems have been running for decades. During those years, almost every major system designed to keep humans alive has malfunctioned at least once. None of those failures were catastrophic because the station is only a few hundred kilometers above Earth. Replacement parts arrive on cargo ships. Crew members can swap out faulty modules. New hardware shows up when the old one degrades. A Mars crew never gets that luxury. No supply ship, no replacement module, no rapid repair. Everything must work perfectly from the moment the engines fire to the moment the crew returns home. But the ISS record lays out how unrealistic perfect operation really is. NASA's closed-loop experiments on the ISS show how difficult it is to recycle water without contaminants building up, how easy it is for carbon dioxide scrubbers to hit saturation levels, and how delicate oxygen generation hardware becomes when it must run non-stop. These aren't small issues. These are core functions that keep lungs breathing, blood oxygenated, and organs operating. On Earth, you don't think about these processes because the atmosphere handles them automatically. On a ship heading toward Mars, the atmosphere is artificial and created by machines that have limits. Any error in that system threatens the entire crew. On the ISS, those errors have been frequent enough to require years of ongoing redesigns. Now, imagine those same failures happening when the ship is millions of kilometers from home. Water recycling in space is one of the biggest challenges because it has to extract every usable molecule from sweat, humidity, urine, and waste streams. The ISS water processor is designed to recover about 90% of the water. Sounds great until you realize that even that 10% gap becomes enormous over a mission lasting years. A Mars crew can't carry enough spare water to make up the shortfall, and even a small loss over time can push the mission toward dehydration risks. But efficiency isn't the weakest part. Reliability is. The ISS urine processor has failed repeatedly throughout its operational life. At one point, the system shut down due to calcium sulfate scaling, a kind of mineral buildup that clogged the machinery. The units required repairs, replacement hoses, reconfiguration of pumps, and manual intervention to keep the system from collapsing. All of that was possible only because the station received a constant supply of hardware from Earth. A Mars crew has no such support. When a closed-loop recycling unit fails, the crew cannot improvise a replacement using common tools. The machinery involves centrifuges, filters, delicate membranes, chemical processes, and pressure control systems. If one part breaks, the whole process stops. Water recycling malfunctions on the ISS never become existential because cargo runs arrive several times per year. Those runs bring fresh water, spare filters, and replacement valves. A Mars ship cannot carry that level of redundancy. Every extra filter weighs something. Every replacement tank weighs something. Every backup module increases the mass budget. Eventually, the ship runs out of margin. NASA's research teams know this. That is why they ran long-duration closed-loop tests to study the reliability of these systems. The conclusion is clear. Even on the ISS, where maintenance teams can fix problems regularly, reliability is still below what a Mars mission needs. Extending closed-loop operation from months to years amplifies every flaw. If the crew runs out of water in deep space, there is no backup. Breathing feels simple, but maintaining safe air on a spacecraft is one of the hardest challenges of all. Humans exhale carbon dioxide continuously, and it doesn't take long before levels become dangerous. On Earth, air disperses CO2 naturally. On a Mars-bound ship, CO2 must be pulled from the cabin by machines that work around the clock. The ISS uses two systems for this: the Carbon Dioxide Removal Assembly, CDRA, and later upgrades like the Advanced Closed Loop System. CDRA was designed to run for long periods, but it has a long list of documented failures. Valves stuck, heaters burned out, sorbent beds became unstable, fans jammed, repairs took hours, sometimes days, often requiring astronauts to remove panels, pull out entire assemblies, and swap burned-out parts. This system breaks down even with regular maintenance, a full toolkit, and Earth-based teams watching sensor logs in real time. A Mars ship travels beyond the reach of rapid monitoring, and onboard systems must function without days of repair work every time something goes wrong, because every hour spent on intricate maintenance is an hour the crew is exposed to rising CO2 levels. A spike in CO2 affects the body fast. Headache, dizziness, cognitive decline, impaired judgment. In space, those symptoms appear earlier because the air volume is small and circulation is artificial. If CO2 rises unchecked for even a short time, the crew will feel the impact long before the numbers reach critical limits. The hardware used to extract CO2 doesn't tolerate dust contamination, changes in humidity, or mechanical wear. Every working component must be handled with precision. These systems can't be redesigned easily because the chemistry behind CO2 extraction requires reaction beds, temperature swings, pressure control, and specific materials that absorb and release CO2 depending on the cycle. If any part fails during a Mars mission, the crew has only two options: repair the unit with limited spare parts, or switch to backups that may not last the entire mission. If those backups fail, the cabin air will gradually fill with CO2 until the crew can no longer think clearly enough to carry out repairs. The fragility shown during ISS operations becomes a critical risk when stretched to multi-year timelines. Oxygen generation sounds straightforward: split water molecules, release the oxygen, and recycle the hydrogen. But the machinery needed to sustain this process is large, energy-hungry, and prone to breakdowns. On the ISS, this job is handled by the Oxygen Generation Assembly, OGA. It conducts electrolysis using high-pressure pumps, membranes, and separators. The OGA has suffered failures related to contamination, component degradation, leaks, and unexpected shutdowns. Engineers on Earth guide the crew through detailed repair procedures to restart the unit. A Mars crew can't rely on outside guidance in real time, and the hardware must run longer than any OGA system has ever run on the ISS. Even short downtime becomes dangerous when the entire air supply depends on it. A Mars ship could theoretically store oxygen tanks, but those tanks add enormous mass, and mass instantly pulls the mission toward launch failures. No spacecraft can carry enough oxygen for the entire mission without overwhelming the mass budget. This means the oxygen generator must work with near-perfect reliability. The ISS record doesn't support that expectation. Repeated shutdowns and maintenance events have shown that oxygen regeneration at long duration is not yet a mature technology. A Mars mission isn't a 6-month cruise with steady conditions. It spans years, and every part of that journey requires a stable life support system that never goes offline. That is a level of reliability no space-based closed-loop system has ever reached. Even if the hardware worked flawlessly, microbial growth, unexpected chemical contamination, or trace compounds from plastics inside the cabin could alter the chemistry of the recycling process. On the ISS, engineers can analyze samples and adjust procedures quickly. On a Mars mission, months of delay make that impossible. The problem becomes sharper when you consider that the crew must live inside a spacecraft with no way to vent large volumes of air into space without losing pressure. The closed-loop system can't just reset itself. It has to stabilize whatever contamination builds up over time. The ISS replaces filters whenever samples show performance drops. A Mars crew can only bring a limited stock. Every part of the cabin atmosphere, from oxygen concentration to humidity, needs modulation by machines that age as the mission progresses. Rubber seals dry out, metal fatigue builds, filters clog, pumps degrade, sensors drift out of calibration. A system surviving for a few months proves nothing about how well it will survive for multiple years. How food turns into a mass problem that won't go away. Food storage for a Mars mission has no easy solution. Humans need calories every day, and food mass doesn't recycle like water or air. Once consumed, it turns into waste that must be processed, but the calories themselves disappear. You cannot recycle calories. The only way to sustain a crew is to bring enough food or grow it. Bringing enough food for years adds tons of mass. Every kilogram adds stress to the launch vehicle. Every kilogram reduces the spare mass available for redundancy. NASA's food systems for space are designed around resupply. The ISS receives new shipments several times per year, bringing fresh food, packaged rations, and replacements for anything spoiling or damaged. A Mars ship receives nothing. Stored food also loses nutritional value over time. Some vitamins degrade within months. Long-duration missions require food that stays stable for years, and most current space rations don't meet that standard without supplementation. These issues aren't theoretical. NASA has documented nutrient decline in stored space food. A mission lasting years exposes the crew to deficiencies unless the ship carries supplements, which add more weight, or unless the crew grows plants. Bioregenerative systems, plants, algae, microbial loops, look appealing because they promise fresh oxygen, fresh food, and natural recycling. But the reality is that these systems are still experimental, unreliable, and difficult to scale. Space agriculture tests on the ISS show encouraging results, but the yields are tiny. Astronauts have grown lettuce, radishes, peppers, and a few other crops. These are symbolic steps, not survival steps. The production rate isn't close to what a crew needs. Plants need space, light, power, water, and strict environmental control. If any of those conditions shift, crops fail. Even advanced systems like hydroponic cabinets require pumps, LED arrays, nutrient cartridges, and root containment. These machines break as well. Supporting an entire crew using plant systems demands hundreds of kilograms of equipment and large internal volumes. Volume that a Mars ship doesn't have. Algae reactors attract attention because algae grow fast and produce oxygen efficiently, but they are unstable ecosystems. They require constant monitoring to prevent runaway growth, contamination, or crashes. Even small deviations in temperature or light can collapse an algae culture in hours. Once that culture dies, the system loses efficiency and may release toxins. NASA has evaluated closed ecological life support systems for decades, and while those studies show future promise, no system has ever operated long enough or with enough reliability to support a Mars crew. Every issue with water recycling, CO2 scrubbing, and oxygen generation becomes magnified when you remove resupply and rescue. The ISS has survived breakdowns because the crew can depend on hardware coming from Earth. A Mars crew loses that safety net the moment they begin the journey. A Mars ship requires systems that work almost flawlessly for years. The ISS has never achieved that level. No prototype has achieved it. No closed-loop test on Earth has run long enough with the same constraints. A Mars mission has no emergency supply cache in orbit, no abort route, no quick turnaround, no ability to call for help. One failure in the loop is enough to threaten the entire mission, and life support doesn't allow slow responses. If the oxygen generator fails, the crew feels the impact quickly. If the CO2 scrubber jams, the crew begins losing cognitive function. If the water processor breaks, dehydration becomes a risk within days. This level of vulnerability is why life support stands as one of the hardest barriers in human Mars plans. Not because the technology doesn't work at all, but because it has never worked with the reliability that a Mars mission demands. The Mars surface is worse than advertised. Across more than 2 decades of research in remote stations, from Antarctica to deep-sea submarines, to high-isolation desert labs designed to simulate the Martian experience, a consistent pattern appears whenever groups remain cut off from the outside world for long periods. People begin to experience a slow tightening of their emotional bandwidth, as daily routine merges with the pressure of being trapped in the same environment without any option for space, privacy, or escape. These environments reveal how the human mind stabilizes itself by drawing energy from social variety, shifting surroundings, random encounters, sounds, smells, and the small unpredictabilities that Earth provides without effort. Once those disappear, the brain starts to operate in narrower loops, and that constriction shows up in ways that can raise major problems for a future Mars crew. Data from long winter cycles in Antarctica records rising irritability, reduced cognitive flexibility, and a growing difficulty in maintaining cooperation during decision-heavy periods. Teams can function, but it becomes a daily push rather than a natural flow, and even minor disagreements expand into tense, enduring conflicts. Submarine crews report something similar, even with strong training, constant mission structure, and access to support. Mars analog missions like High Seas in Hawaii and Mars 500 in Moscow documented how groups who begin their missions in sync gradually lose rhythm as the weeks turn to months and the months turn to long cycles without real sunlight, fresh air, or new emotional input. In 2024, an extensive study confirmed that long-term isolation does more than trigger mood changes. Brain scans taken before and after long isolation missions revealed physical shifts in areas tied to memory consolidation and spatial processing, as if the brain slowly reorganized itself to survive monotony and stress at the cost of flexibility. This means a crew on Mars wouldn't just feel stressed. Their cognition could slowly reshape under stress, and those changes might not reverse easily during the mission. None of this is hypothetical, because we already see it in people living through conditions that are far milder than what a Mars crew would endure. Mars adds new layers that none of these analog missions can replicate. A crew on Earth knows evacuation is possible. A helicopter or a supply aircraft can reach Antarctica. A submarine can surface. A desert habitat can open its door. On Mars, evacuation is impossible. There is no rescue ship parked nearby. There is no launch window ready to bring them home. Every crisis must be solved by a small group who are already carrying the mental drain of an isolation environment far harsher than anything on Earth. Even small interpersonal conflicts can turn mission-threatening when the group has no mental space, no outside stimuli, and no psychological exit door. The Martian day is slightly longer than Earth's, but that extra 40 minutes creates irregular sleep drift that compounds over time. Experiments on Earth show how sensitive human circadian systems are to light cues and environmental cues, and the Martian surface provides none of the frequencies or intensities the human body evolved to use. Artificial lighting can approximate Earth's pattern, but crews still report irregular sleep timing, fragmented rest, and lower quality recovery in isolation environments. On Mars, where every task demands precision, clear thinking, and fast reaction time, cumulative sleep disruption introduces real risk. Even with the best training, even with stable mission plans, even with excellent equipment, humans on Mars face psychological and cognitive challenges that Earth's most extreme environments can only partially reveal. Records from those environments already show that cooperation can crack under pressure, and Mars multiplies the pressure by adding conditions that turn every mistake into a disaster, every disagreement into a distraction, and every day into a test of endurance with no external support. Martian temperatures swing across ranges that strain equipment and human tolerance alike. At the equator, where sunlight hits most directly, temperatures can rise to around 20 degrees Celsius for short spans. Those mild peaks appear in documentaries and public talks because they make the planet feel reachable. But those warm points occur in small pockets that fade rapidly because the planet's thin atmosphere cannot hold heat. As soon as the sun shifts, the temperature can crash toward -70 or -80 degrees Celsius, and at night, the cold sinks toward -100. At the poles, readings have dropped toward -128. This means every structure, suit, cable, pipe, joint, circuit board, and battery must handle wide thermal swings daily. The human body has no capability to regulate in an environment like this without a full suit at all times, and any failure in that suit becomes an immediate emergency. The dust storms complicate everything. Some storms stretch across small regions, but others grow until they blanket the entire planet. Sensors on orbiting spacecraft have watched the red surface vanish beneath weeks-long sheets of wind-borne dust, thick enough to reduce visibility to almost nothing. These storms don't always involve strong surface winds, but they fill the air with fine particles that cling to every surface, block light, reduce power generation, and raise maintenance workloads dramatically. Solar panels lose output as dust builds layer after layer. Any habitat relying on solar charging would see days or weeks of low power and would need constant manual cleaning, which places astronauts outside in dangerous conditions. Dust on Mars is not just a nuisance, it is chemically active and physically harmful. Samples examined by landers and rovers reveal that Martian soil contains perchlorates, which interfere with thyroid function and are toxic when inhaled or consumed. The dust also carries micro-sharp fragments created through billions of years of erosion in a low-pressure environment. These shards are small enough to enter suit joints and seals, causing abrasion that accelerates wear. If astronauts inhale them during suit ingress or habitat transitions, the fragments can reach deeper areas of the lungs, where they cause long-term damage and inflammation. Pressure adds another critical hazard. The atmosphere on Mars is less than 1% of Earth's. At that pressure, unprotected human tissue would not survive. A tear in a suit, a faulty seal, or a puncture from debris would cause rapid decompression. Even small failures become life-threatening because the pressure difference is extreme. Every activity outside the habitat turns into a carefully calculated risk because the margin for error is razor thin. Equipment must maintain its integrity across long durations without the benefit of abundant repair supplies or replacement parts. Water exists beneath the surface, mainly locked in ice that blends with the surrounding regolith. It is not waiting as liquid pools or accessible streams. Extracting this ice requires heating, crushing, and processing large quantities of soil, and even then, the water must be purified from perchlorates and dust contaminants. This process demands high energy output, heavy equipment, and consistent maintenance, none of which can break down for prolonged periods. Rovers like Curiosity and Perseverance have given detailed measurements of surface radiation levels, showing that Mars receives constantly elevated doses from cosmic rays and solar particles. Even though radiation is the focus of other sections, here on the surface it becomes an unavoidable physical condition. Habitats must be buried or shielded heavily, Suits must protect at levels far beyond Earth's expectations, and daily tasks must account for increased exposure. Every meter of the Martian surface behaves like an environment built to test every component of human hardware. Temperature swings strain materials, dust reduces power and wears down joints. Perchlorates threaten both equipment and human health. Pressure threatens survival at every second. Water extraction demands complex machinery, and the radiation bath adds another constant risk. While Mars appears calm in images, the reality is an unsteady blend of silent hazards that do not fade, do not pause, and do not allow routine to settle. A world where every crisis must be solved by the crew alone. Throughout decades of isolated research environments, a trend emerges that shows how group dynamics can shift when faced with ongoing stress. On Mars, these shifts carry heavier consequences because there is no space for errors, no backup team nearby, and no ability to fly in supplies. Living in a confined space for years affects how people communicate, how they share responsibilities, and how they maintain patience when confronted with workloads that never shrink. Small frustrations in closed environments grow slowly, and if left unaddressed, they can escalate into communication breakdowns. Records from Antarctic winter overs show how groups sometimes split into smaller subgroups with competing approaches to the same tasks, leading to internal disagreements that consume more time than the tasks themselves. Mars analog missions documented similar patterns, including emotional withdrawal, deteriorating motivation, and non-cooperative behavior during stressful phases. On Mars, where every decision carries physical risk, poor group cohesion can lead to mistakes that spiral into far bigger problems. Sleep disruption only amplifies this. The Martian day's slightly longer cycle does not synchronize naturally with human circadian rhythms. In environments without Earth's sunlight, crews showed drifting sleep timing, meaning they gradually woke later and later each day until schedules needed artificial resets. When the mind is tired, disagreements become sharper, problem-solving becomes slower, and emotional resilience collapses. A Mars crew cannot rely on rapid communication with Earth. The delay ranges from 4 minutes to almost 24, meaning even simple questions require long waits. There is no situation where Earth can make fast decisions for the crew, no way to coordinate emergencies with real-time accuracy, and no possibility for immediate remote intervention. When equipment breaks, the crew must diagnose it alone. When someone gets sick, the crew must handle it alone. When the air system malfunctions, the crew must repair it before conditions deteriorate. Earth can advise, but the final responsibility rests entirely on the small team that is already navigating psychological strain, environmental hostility, and long-term fatigue. Group cohesion becomes more fragile in proportion to resource scarcity. On Mars, water extraction is slow, food storage is finite, and energy generation depends heavily on hardware that must operate under relentless dust and temperature shifts. Every shortage creates tension, and every tension can grow faster in isolation. And since habitat interiors are small, personal space disappears. There is nowhere to retreat. People breathe the same recycled air, hear the same mechanical noises, see the same walls, and work with the same companions every day. Mars gives no second chances. Decisions must be correct the first time. Repairs must succeed with whatever tools the crew brought with them. A malfunction that would be inconvenient on Earth can become fatal on Mars. Even a minor crack in a pipe or a valve can cascade through the life support chain, reducing oxygen or water supplies, forcing crews to stop other tasks to focus on emergency repairs. And because the surface conditions promote corrosion and abrasion, suits, seals, and equipment wear faster than they would in controlled settings. Curiosity and Perseverance have recorded radiation levels significantly higher than Earth's surface, which affects both human health and equipment longevity. Electronics degrade faster under high radiation environments, sensors can fail, and computer systems need shielding that adds weight and complexity. All of these challenges converge into a tight band of survival that stretches across years, with no outside help and no option to abandon the mission if conditions worsen. the thin atmosphere that betrays every calculation. Mars's atmosphere is a trap. At first glance, it looks like a solution, a layer of gas that could slow a descending spacecraft and reduce the need for heavy propulsion systems. In reality, it is neither a proper cushion nor a vacuum. It is the worst of both worlds. A spacecraft cannot rely on parachutes alone because the air is too thin to provide enough drag to slow a massive ship carrying humans, fuel, and supplies. On Earth, parachutes work predictably because the air can hold them and generate steady resistance. On Mars, the same parachute generates far less drag and requires a larger surface area that becomes structurally challenging to deploy at supersonic speeds. The so-called 7 minutes of terror experienced by robotic missions like Curiosity and Perseverance becomes vastly more complicated for humans. Those 7 minutes were nerve-wracking for engineers controlling 900-kilogram robotic rovers. Multiply that mass by 50 or 100 to include crew, life support, supplies, and return fuel. And the physics of entry, descent, and landing starts breaking every known assumption. Every kilogram added to the ship exponentially increases the difficulty of slowing down without shattering the craft. Atmospheric drag alone cannot compensate for the added momentum, and rockets used for retropropulsion must scale in size, weight, and fuel mass in ways that are barely feasible. Every Mars mission across decades shows this reality. Historical failure rates hover near 50% for landing attempts, and that includes the entire range of landers, rovers, and orbiters. Failures are not abstract. They are catastrophic. Crash landings, tip-overs, or explosions occur because a slight miscalculation in speed, angle, or atmospheric density propagates through the system. Robotic missions already carry extensive redundancy, but humans require orders of magnitude more safety margin. That safety margin adds mass, and mass drives every aspect of the landing challenge, from parachute strength to engine thrust. Even supersonic retropropulsion, where rockets fire downward to slow descent in the upper atmosphere, is limited by materials, fuel efficiency, and control systems. Retropropulsion requires perfectly balanced thrust vectors. Any unevenness risks tilting the ship and turning a controlled landing into a fatal crash. The atmosphere's variability, temperature differences, and dust density all interfere with rocket behavior. Designing engines that can fire precisely under these conditions without failing for months of travel and years of storage pushes current aerospace engineering to the edge of its capabilities. Temperature swings compound the problem. The spacecraft must survive entry heat from tens of thousands of kilometers per hour, then endure surface cold, which can drop below -120 degrees Celsius at night and remain below -60 during the day in most regions. Thermal protection systems, heat shields, and insulating materials all experience expansion, contraction, and degradation under repeated stress. Even advanced materials, tested on Earth for decades, are brittle when exposed to repeated cycles of extreme heat and radiation combined. Parachutes, heat shields, and retropropulsion engines are no longer individual components. They become part of an interdependent, fragile chain. If one fails, the mission fails. And unlike Earth, there is no second attempt. Launching humans means the risk of failure multiplies with mass, and the requirement for safety multiplies the mass again. The thin Martian atmosphere punishes both sides of the engineering spectrum. Too little drag for slowing, and too much interference for precise rocket control. Each second in descent is a struggle against physics that refuses compromise. Structural fragility under Martian conditions. Even after the spacecraft touches the surface, the battle is far from over. Landing requires the ship to survive while supporting habitats, life support systems, and equipment that must operate for years. The surface is hostile to all materials. Mars dust, fine and sharp, infiltrates every joint and seal, abrading and accelerating wear. Temperature swings create microcracks in metals and composites, while radiation damages polymers, weakening the hull over time. Habitats made from 3D printed regolith are promising for reducing launch mass, but tests show brittle behavior, limited pressure containment, and susceptibility to thermal cracking. A crack in a habitat wall is not repairable overnight. It is a slow escalation towards structural failure if pressure, temperature, or impact stress shifts. Power systems face similar fragility. Solar panels degrade with dust accumulation, reducing energy output during storms that can last weeks and cover the entire planet. Nuclear reactors, while stable, carry their own transport risks, as they must survive launch, transit, and Martian surface placement without leakage or critical malfunction. Even with robust systems, radiation and dust slowly damage electronics, wiring, and sensors, making long-term maintenance unavoidable. Crews must constantly monitor, clean, and repair, adding hours of labor to every day, often under the same hostile conditions that threaten the structural integrity of their living spaces. Air leakage and habitat fatigue are constant threats. Reduced gravity means joints and fasteners flex differently than expected. Every opening for airlocks, conduits, or windows creates stress points. Over time, repeated pressure cycles wear seals, leading to micro-leaks that may not immediately be detectable but slowly reduce cabin integrity. The habitat must hold breathable air, water recycling pressure, and structural loads from equipment and furniture, all while resisting temperature extremes and dust intrusion. Every kilogram of habitat mass translates into additional fuel for launch and landing, which circles back to the problem of landing difficulty. Shielding habitats from radiation adds another layer of mass. Effective protection requires either meters of regolith covering or tens of tons of built material. Every ton added to the landing system forces engineers to recalculate descent velocity, parachute size, retro-propulsion timing, and landing site stability. The scale of mass for shielding multiplies the difficulty of landing exponentially, creating a cycle where each requirement for safety or durability increases the technical complexity and risk of failure during descent. Even the simplest maintenance becomes life-threatening. Moving outside for repairs exposes astronauts to radiation, temperature extremes, and low pressure. Inside the habitat, dust permeates electronics, food storage, and water systems, making continuous cleaning and monitoring unavoidable. Systems designed for Earth-based repairs cannot function autonomously for long periods under Martian surface conditions. Each solution introduces new problems. Each repair adds risk. Every day is an engineering test on multiple fronts simultaneously. Landing on Mars is ultimately a problem of mass and energy. Every kilogram carried, whether fuel, shielding, habitat material, or life support redundancy, increases the energy required for deceleration, descent control, and surface stabilization. Propellant mass follows a logarithmic relationship, meaning even small increases have massive effects on total launch weight. Engineers must optimize every component, but optimization cannot eliminate the fundamental physics of kinetic energy and momentum. The paradox is that mass is required to survive the surface, but landing heavier increases risk. Rockets capable of supersonic retropropulsion must carry additional fuel, and that fuel increases weight further, creating diminishing returns with every safety improvement. Thermal protection must scale with both entry speed and mass. Parachutes must scale with both surface area and mass. Life support systems, shielding, and habitats all add more weight, looping back into the same problems that make landing difficult in the first place. Power systems are constrained by mass and efficiency. Solar panels must survive dust and storms while providing enough energy for life support and repairs, but larger panels add more weight to the descent. Nuclear reactors can supply consistent energy but cannot absorb the shocks, vibrations, and handling stress of Mars landing and long-term deployment without additional shielding, transport structures, and safety measures. Each kilogram added to ensure system survival multiplies the landing challenge again, creating an unforgiving cycle of interdependent constraints. Materials themselves face a lifetime of degradation before the crew ever steps onto the surface. Radiation weakens polymers and metals. Dust abrades every moving part. Thermal swings expand and contract structural elements daily, potentially causing fatigue cracks over months or years. These effects cannot be ignored because the mission duration is measured in years, not days. Every material choice is a compromise between mass, durability, and the ability to land safely on a planet that refuses to slow down for human needs. Historic landings provide context. Robotic missions fail at rates near 50%. Every failed probe represents lessons learned, but human missions cannot tolerate failures. Scaling landing systems from small, lightweight rovers to human-rated ships is not linear. Parachutes and retro-propulsion systems do not simply get larger. They require entirely new materials, deployment mechanisms, and testing that has never been conducted at the necessary scale. No simulation, no Earth-based test, and no vacuum chamber can perfectly replicate the combination of low pressure, dust storms, extreme temperatures, and long-duration stress cycles that the Martian surface imposes. SpaceX and the private sector reality. SpaceX built its reputation on fast progress, bold timelines, and the idea that moving quickly can solve any problem thrown at the company. That approach works when rockets carry cargo or satellites, because each mission provides data that feeds the next iteration. It works when a failed booster becomes a learning tool. It works when a launch pad explosion is treated as a setback rather than a tragedy. The moment humans enter the picture, everything shifts. Failures stop being data points and start becoming unacceptable. Starship was designed from the start to be a giant leap toward human deep space travel, a ship with enough volume and power to carry crews across interplanetary distances. Yet the distance between what the vehicle promises and what it can safely do keeps widening. Many of the obstacles are not small technical bugs, but fundamental engineering challenges wrapped inside Starship's core design, and the pace of testing has shown how hard these problems are to untangle. The most talked about difficulty hides inside the heart of the vehicle, the Raptor engine. SpaceX needs dozens of these engines to work together, each producing enormous thrust in a narrow pressure window. Unlike older engines that rely on simpler cycles, the Raptor uses a full-flow staged combustion design that pushes temperature, pressure, and materials to their limits. On paper, this cycle gives higher performance, but it also creates new weak points. Overheating, combustion instability, and vibration become far more serious when multiplied by several dozen units strapped to one stack. Each failure during tests shows how sensitive the design is. Any crude system built around dozens of high-stress engines needs an extremely stable version of that engine. Yet the long stream of tweaks shows that reliability was never guaranteed. Building one engine that behaves well for a short test is one challenge. Building 30 or more identical engines that behave exactly the same under full load on launch day is another level entirely. Once the engine's light, Starship faces another area of constant trouble: its heat shield. Every tile must stay in place during ascent, survive vibrations, absorb heating during re-entry, and resist cracking or shedding. A missing tile is not a cosmetic issue on a vehicle that returns from orbital speeds. A small gap grows into a path for plasma, and plasma tears through steel in seconds. Even cargo missions cannot afford tile shedding, but human missions need consistency far beyond that. The company has spent years trying to secure tiles so they remain locked through shaking, temperature swings, and aerodynamic stress. Each launch has revealed spots where tiles detach, fracture, or shift. This forces long inspection cycles after every flight, defeating the idea of rapid reuse that Starship relies on. The challenge is not simply gluing tiles better. The vehicle's steel skin expands and contracts during flight, bending in complex ways that are hard to predict. Any tile system must adapt to that movement while still surviving re-entry. So far, the perfect combination has not been found, and every time tiles fail, the repair teams face the kind of work that makes fast turnaround nearly impossible. The heat shield problem links directly to the reality of a ship designed for interplanetary flight. SpaceX wants to send Starship on long journeys, but the vehicle remains vulnerable to deep space conditions. The steel hull gives some durability, yet on a long-duration mission, it offers little protection against cosmic radiation and solar storms. Engineers understand the risk. Radiation levels beyond low Earth orbit rise quickly, And shielding requires mass that Starship is not built to carry. To properly protect a crew for months in space, a ship needs either thick walls or a specialized shield section with dedicated mass. Every kilogram reduces payload, yet without enough shielding, crew health drops fast. Starship's design chases high payload capacity, but high capacity means thin structural materials and minimal shielding. That trade-off does not go away with optimism or testing. It demands major redesigns, which slows everything. Another major gap sits in the fuel plan. Starship cannot reach Mars without refueling in orbit, and the entire mission concept rests on large-scale propellant transfer. No agency or company has ever moved cryogenic propellants in large quantities between two massive vehicles in orbit. Small experiments have proven that liquids can move in microgravity, but controlled transfer of huge volumes has its own issues. Propellants boil off in space, and keeping them cold requires power and insulation. Connecting two massive tanks in orbit without leaks or freezing valves is far harder than the public statements suggest. For human missions, the connection must seal perfectly. The flow must remain smooth. Tanks must remain stable. Pumps must work without vibration damage. None of this has been demonstrated at any scale that resembles what Starship actually needs. Without this capability, the entire Mars dream stops, because Starship cannot carry enough fuel on its own for a complete journey. The private sector timeline worsens the pressure. SpaceX has always promoted aggressive schedules with the idea that ambition drives progress, but the constant slips in 2024 and 2025 reveal how many pieces of the program require new solutions that will take years to mature. The company launched several major test flights, yet each answered one question while raising many more. Heat shield tiles fell. Raptors shut down early. Stages separated but not cleanly. Boosters landed hard or never attempted landing. Some tests reached orbit for short periods, but controlled re-entry remained out of reach, and the mass cases used during tests were nowhere near crewed weight. Subsystems designed for long-duration use never face space exposure for more than hours. All these gaps create more work for engineers attempting to move the program to the next milestone. SpaceX also values something it calls rapid iteration, a method that works efficiently when hardware is inexpensive and explosions are accepted. That mindset breaks down with human certification. Agencies that approve human flights demand extremely slow, careful reviews. Every part must meet strict standards. Every launch must go through layers of checks. Failures cannot be written off with phrases about learning opportunities. Private companies must follow the same rules, but the fast-paced culture at SpaceX does not align with the tempo required for human safety. A rocket that explodes teaches SpaceX a lesson, yet a rocket that carries humans cannot explode even once. These differences become clearer as more test flights show how sensitive Starship remains to small errors. Starship's mass challenge. Starship's mass adds another long-term challenge. A vehicle of this size is difficult to control, difficult to land, and difficult to support. The booster alone is heavier than anything flown in history. The ship stacked on top adds even more complexity. The large mass amplifies every vibration and every structural strain. To land safely, Starship must conduct controlled burns using multiple engines that have to ignite at the right moment. A single delayed ignition can cause an impact hard enough to break the structure. On Earth, this is dangerous but manageable near a controlled pad. On Mars, with weaker atmospheric braking and less margin for error, the challenge grows. SpaceX must prove the ship can handle landing loads every time, with no second chances for crew. This problem links to propellant transfer, because landing on Mars requires fuel reserves carefully balanced across the flight profile. Miscalculations quickly cascade into unsafe conditions. SpaceX argued that stainless steel offers strong thermal properties and lower cost. Those points remain true, but the material has drawbacks. It handles heat well, yet it transmits vibration and sound easily. Building a large crew cabin inside a steel hull leads to issues with noise, stress, and fatigue. Long-term exposure to microgravity already weakens the human body, and vibrations amplify internal stress. A crewed vehicle needs interior damping, radiation shielding, water storage, and equipment racks that anchor firmly without becoming damage points. Starship's interior volume looks vast, yet that space must host life support machinery, power systems, storage, redundancy, furniture, and emergency shelters. Every added system increases mass, and mass pushes the engines harder. These trade-offs continue throughout the design process, with no simple answer. Moving toward real missions demands reliability, but the 2024-2025 timeline was filled with launch delays and redesigns. Some delays came from the FAA process, others from engine supply issues, and others from tile problems. Each delay affects downstream plans: propellant depots, tanker flights, launch pad upgrades, payload preparation, and long-term crew module development. Private companies rely on consistent test schedules to keep investors confident, and constant slips make future funding more complicated. If timelines stretch out too far, other agencies or competitors shift focus or reconsider joint plans. The belief that iteration will always win meets a harsh wall when human safety enters the equation. A company cannot test human-rated systems by blowing them up repeatedly. Regulators demand redundancy, fault tolerance, and design stability. That means years of slowly proving that every system can run flawlessly. SpaceX can maintain bold public goals, yet realistic human certification pushes many of those dates out by years or decades. Even small failures inside an engine or heat shield tile system mean full reviews, redesigned parts, and more test flights. Nothing moves quickly when human life is involved. The private sector advantage lies in flexibility, but sometimes too much flexibility slows progress, because designs change faster than they stabilize. A heat shield that gets reworked every few months cannot build a safety record. An engine altered after every test cannot qualify for human use. A fuel transfer system still on paper cannot support real mission planning. Starship's many redesigns show a company searching for solutions, yet constant change also delays the slow, steady verification process that human missions demand. SpaceX can make fast jumps during development, but human flights do not allow shortcuts. Starship's landing systems fit this pattern. The ship relies heavily on belly flop descent to lower speed before engine ignition. This maneuver requires perfect control. A small deviation snowballs quickly. For cargo, this can be tested repeatedly until tuned, but for humans, it requires far more certainty. Landing a heavy ship vertically on steel legs with engines firing at the last moment leaves little room for mistakes. Even small dust clouds on Mars can block sensors, interfere with readings, or complicate ignition timing. Until the system shows a flawless streak of landings under varied conditions, the idea of trusting it with a human crew remains distant. Beyond landing, Starship must support life for long durations. The company has shown early mock-ups, yet none of these demonstrate real functionality. A deep space ship must run closed-loop environmental systems reliably for months. It must shield crews from radiation storms. It must store food and water with long shelf life. It must include emergency shelters, medical equipment, and enough power to run everything continuously. Starship has large internal space, but space alone does not guarantee habitability. Once systems are added, the mass grows, reducing available margin. The more mass added, the more fuel required. The more fuel required, the more tanker flights needed. Every increase cascades across the entire mission architecture. Even the booster stage faces steep challenges. The Super Heavy booster uses dozens of engines firing at once, making it the most complicated first stage ever built. Each launch tests engine alignment, vibration control, and throttle coordination. A small imbalance becomes dangerous quickly. Guidance systems must direct this massive tower through ascent, stage separation, and return. The return burns must ignite on time with perfect throttle control. Landing legs must deploy reliably. A booster this large has no simple fallback mode, and human missions require far wider safety margins than cargo missions. Flight after flight has shown how complex these interactions are. The launch infrastructure adds more pressure. Starship requires a specialized tower and strong ground systems. Each time a launch fails, debris spreads across the area, requiring cleanup and inspection. As safety requirements rise, the tolerance for pad damage decreases. Human missions demand pristine conditions. Rapid launch scheduling becomes nearly impossible because every test flight stresses or breaks parts of the pad. The ground support equipment must match the ship's scale, and every redesign slows operations. On top of these technical hurdles, radiation protection remains one of the hardest problems to solve for any deep space mission. Starship's thin steel hull does not stop high-energy particles. Crews would require shielding materials like water, polyethylene, or specialized composites. Carrying enough of these materials adds significant mass. Some designs propose placing water tanks or cargo around sleeping areas, but this rearranges internal space. Every part of the ship becomes a trade-off between comfort, protection, storage, and weight. With Mars missions lasting months, shielding cannot be treated as an afterthought. Until a clear shielding solution is locked in, crew safety remains uncertain. Power systems add another layer of difficulty. Starship will need long-duration power sources for deep space missions. Solar panels help, but panels degrade, accumulate dust, and lose efficiency. Nuclear sources offer stable energy, yet shipping a reactor safely presents major regulatory and technical challenges. Private companies face strict rules when handling nuclear material. Until a reliable power plan is finalized, life support and communication systems lack guaranteed long-term operation. Inside the spacecraft, redundancy must be built into almost every system. Human crews need backup controls, duplicate life support loops, multiple communication paths, and emergency hardware. Starship's current configuration shows early concepts, but not the full redundancy stack required for safe interplanetary travel. Each redundant system adds mass, power demand, and maintenance requirements. Engineers must balance these needs without compromising launch mass limits. Testing becomes harder as systems grow. Early prototypes solve propulsion and structure issues, but human-ready prototypes must test environmental control, air quality, temperature control, humidity, waste management, storage systems, emergency shelters, and radiation shielding. These tests cannot be rushed. They demand long-duration trials in orbit. Rapid iteration does not help when testing requires months of steady performance. Safety standards from agencies like NASA require years of paperwork, verification, and analysis. Every bolt, pipe, panel, cable, and tank must be documented. Private companies can design quickly, but human certification moves at a much slower speed. This creates a conflict between the pace SpaceX prefers and the pace regulators require. Starship cannot skip this process. SpaceX often presents Starship as reusable, but high reusability demands extremely durable components. Rockets that return from orbital re-entry suffer stress, heating, and material fatigue. The more flights a ship performs, the more its structure must resist microscopic damage. Cargo missions can allow occasional part swaps, but human missions need consistent reliability. Reusability becomes expensive because replacing worn parts takes time, and the ship must be inspected down to fine detail after every mission. The private market adds unpredictable factors. Investors want fast progress and clear milestones. Slower timelines reduce confidence. Funding shifts as delays grow. Companies sometimes prioritize visible achievements rather than slow-moving background work. When mission-critical subsystems require years of refinement, public pressure conflicts with engineering reality. Starship's exterior tiles are another challenge. Temperature swings during launch, orbit, and re-entry stress the attach points. The ship shakes during ascent. Steel expands under heating. Tiles fall or crack when movement exceeds design tolerances. Every re-entry test reveals new areas of weakness. Until tile performance becomes consistent, the ship cannot safely return from orbit with a crew. Even the ship's steering fins must withstand intense aerodynamic stress. These fins control orientation during descent and belly flop. They move under enormous load. Their hinges, motors, and actuators must operate flawlessly while experiencing heating, pressure changes, and vibration. A jammed fin would cause loss of control. Engineers test designs repeatedly, yet consistency across dozens of flights remains a long process. Inside the ship, life support systems must handle humidity, CO2 buildup, heat, and odors. Filters must remain clean. Airflow must stay smooth. Microbial growth must be monitored. Water must be recycled. Waste must be processed without smells or leaks. A system that works for a week in a test chamber must work for months in space. This requirement cannot be met with quick iterations. It requires long-term reliability. The private sector approach tends to assume that enough tests will eventually solve all problems. This is true for cargo vehicles because losses are acceptable. Human missions cannot afford losses, and this changes everything. True safety requires extremely slow verification, not rapid trial and error. SpaceX must adapt its culture to meet that reality. The delays from 2024 and 2025 highlight how many issues remain open. Each test flight brought progress, yet each also showed how far the system is from being human-ready. Engines shut down early, stages separated with rough behavior. The ship survived heating but lost tiles. Booster landings failed or were not attempted. These results show a vehicle still in early development, not one nearing crew capability. Propellant depots, vital to the Mars plan, remain concepts. Tanker flights will need to be precise. Docking must be stable. Orbit must be predictable. Propellant must stay cold. Boil-off must be controlled. None of these have been demonstrated. Without depots, the entire Starship architecture collapses for long-distance missions. Private companies can introduce new ideas quickly, but interplanetary travel does not reward shortcuts. Every part of the vehicle must withstand months of activity without resupply. The ship must carry repair kits, spare parts, tools, and replacement filters. Mass grows with each added item. Engineers must decide what to bring and what to risk leaving behind. The real cost: trillions, not billions. When people hear that a Mars mission will cost money, they imagine something similar to previous space programs. They picture budgets that run into a few $1 billion spread over many years. And since space exploration has always sounded expensive, they expect those numbers to feel large, but not impossible. The trouble is that the early figures do not show how big the real cost becomes once every part of a full-scale Mars campaign is added. NASA's own internal studies have shown repeatedly that the price jumps from billions to trillions once long-term needs are added. Designing a mission concept on paper is one thing, yet building everything at the scale required for repeated launches, continuous support, and full crew safety is a completely different reality. These hidden numbers sit in the background of every discussion about Mars, and they explain why progress has stalled for decades, even though engineers understand the physics and know the steps. Each system needed for a human Mars mission is expensive on its own, but when stacked together, they form a financial load no country has been willing to carry. NASA has published cost models for heavy lift rockets, deep space vehicles, landers, habitat modules, life support systems, surface power stations, communications networks, radiation shelters, and return vehicles. Every one of these systems requires a supply chain, constant testing, repeated redesigns, large teams, years of logistics, and specialized facilities. The moment these costs are added into a single program instead of standing alone as isolated projects, the total rises at an astonishing pace. NASA's own internal estimates for a full multi-launch Mars campaign have ranged from $1 trillion to several $1 trillion, depending on the length of the mission, the number of crew rotations, the redundancy built into each component, and the duration of surface operations. These numbers never appear in public because they overwhelm people, yet they sit inside planning documents, technical reports, and congressional briefings. A human Mars mission cannot use a single rocket launch. It requires dozens. Fuel depots must be placed in orbit and resupplied. Cargo landers must travel ahead of the crew. Habitats must be prepositioned. Power systems must be delivered. Emergency shelters must be placed. Crew vehicles must be tested through multiple dry runs. A safe return vehicle must already be waiting on Mars long before humans depart Earth. This kind of operation cannot be done cheaply because each launch multiplies the cost of the entire timeline. NASA's modeling shows that a single crewed Mars mission with minimal safety margin would require multiple heavy-lift rockets per year for more than a decade. Every rocket costs billions. Every support system costs billions. When combined with years of staff pay, testing, manufacturing, and operations, the program's budget climbs so high that even the US government struggles to justify it. When NASA tested the multi-launch mission concept in the early 2000s, the price reached levels that made the administration refuse to support further development. When the agency updated the estimate again in the 2010 S, the cost grew even higher. These numbers did not come from imagination. They came from detailed planning, engineering studies, safety models, launch rate projections, and risk assessments. Even when planners tried to reduce the program to its bare minimum, the price tag never fell into a range that fit the budget cycles of any US administration. The resources needed to send humans to Mars stretch across not just years, but decades. And decades of spending require a stability that political systems do not offer. Now combine these costs with the global funding limits on all space agencies. NASA receives an annual budget that looks large on paper, but shrinks quickly once divided among dozens of programs, centers, and long-term obligations. ESA receives even less when compared to NASA. JAXA, CSA, and the national agencies of other countries have smaller budgets and cannot commit to long-term programs at the scale needed. Even if all the world's agencies combined their Mars budgets, the total would not be enough to sustain a multi-trillion-dollar mission over 20 to 30 years. Space agencies operate inside national politics, and national politics respond to voters who often prioritize healthcare, infrastructure, security, education, economic programs, and immediate concerns over distant scientific missions. This makes long-term planning difficult, even when the science is inspirational. The reality of political cycles and why massive missions collapse before they mature. A Mars program cannot be built in a single presidential term or even two. It requires 3 decades of consistent spending without interruption. Every component must be built, tested, refined, and launched on a strict schedule. Every subsystem must meet safety requirements. Every heavy-lift rocket must fly frequently without gaps. Government programs do not enjoy this kind of stability because political cycles reset priorities. Members of Congress change, administrations change, budgets shift. A plan agreed upon by one set of leaders can be cancelled by the next because long-term programs do not produce immediate results that governments can showcase to voters. The history of spaceflight shows how common this problem is. The Apollo program pushed human spaceflight forward, yet the series was cancelled before it could complete its final missions. Not because the hardware failed, but because the political interest evaporated once the symbolic goal was met. Congress cut funding, NASA scaled down operations, and missions that were already planned and hardware already built were scrapped. This experience remains a powerful warning inside NASA. Success does not guarantee program survival. If Apollo, an extremely popular and world-famous program, could be cancelled while it was still functioning, then a Mars program with a price tag many times larger has even less protection. The Constellation program offers another example. This was NASA's attempt in the 2000s to return to the Moon and then move outward toward Mars. It consumed years of planning, billions in early development, entire supply chains, and multiple aerospace companies working together. After years of progress, it was cancelled during a budget realignment. Engineers who had spent years preparing vehicles, flight systems, and designs suddenly found the project frozen. Hardware became obsolete before ever reaching flight. The cancellation happened not because the engineering failed, but because political leadership changed and the cost no longer matched the new administration's priorities. This pattern repeats often in government-funded aerospace. Programs start, shift, shrink, or vanish entirely because space does not produce immediate political rewards. A Mars program requires funding that outlasts presidents, outlasts Congresses, outlasts economic cycles, and outlasts shifting priorities. No major government has ever shown the ability to maintain decades of uninterrupted commitment at this level. Even nuclear submarine programs, interstate highway systems, and military modernization cycles face delays when leadership changes, and those programs offer immediate national benefits. A Mars program does not create immediate results for voters. It does not solve domestic issues. It does not offer short-term wins. Even if the engineering stayed on track, the budget cuts would likely hit the program before completion. Mars missions also demand steady funding increases every year from the moment planning begins until the mission launches. This is different from smaller science missions that fluctuate. A Mars program cannot survive a cut or a pause once it starts. A funding gap could disrupt manufacturing, stall supply chains, end test flights, delay infrastructure, and force teams to be broken apart. Once a skilled workforce disperses, restarting the program becomes nearly impossible. Congress rarely commits to this type of long, steady spending. The same goes for international partners, who also face internal political cycles and public pressure. When the International Space Station was built, it required decades of planning and construction, yet the ISS was still far cheaper than a human Mars mission. Even then, it barely survived multiple political cycles and faced cancellation threats repeatedly. When the Space Shuttle program experienced cost overruns, safety concerns, and delays, NASA struggled to secure funding. The agency's history is filled with examples where programs were cut even after major investments. This is the environment the Mars program would need to survive in for 30 years without a single misstep. Budget documents offer a clear picture of the challenge. NASA's annual budget typically sits around the same range year after year. A Mars program would require stretching that budget to levels far beyond anything seen in modern times. Past Mars mission concepts assumed a stable NASA budget, but reality shows that budgets fluctuate. Sometimes NASA receives a small boost, other times it faces cuts. These shifts might not seem dramatic from outside, yet inside the program, they can derail schedules and threaten entire mission phases. No long-term plan can run under constant uncertainty. International collaboration faces similar problems. The European Space Agency must gather funding from member nations whose priorities change often. JAXA and CSA have limited budgets. China has long-term ambitions, but also must balance internal economic pressures. Russia faces its own set of budget and reliability issues. No nation or alliance has proven willing to commit to the sustained funding level required for a 30-year Mars program. Even proposals for joint global missions fall apart once cost discussions begin. Countries support science missions that cost hundreds of millions, or small flagship missions that cost a few billion. Yet none have stepped forward to support a program costing trillions. A full crewed Mars mission is not just about reaching the planet. It demands a supply chain, reaching from Earth's surface to Mars orbit and then down to the surface. It requires heavy cargo landers, capable of delivering equipment ahead of the crew. It requires surface habitats engineered for radiation protection. It requires power systems capable of running continuously for years. It requires landing pads, communication towers, life support units, spare parts, backup units, emergency shelters, and return vehicles. Each one must be tested extensively. Each one must be launched many times. Every launch costs money, and when dozens of launches are required, the totals reach levels that would strain even the strongest economy. A multi-trillion-dollar program does not just stretch budgets, it reshapes them. To fund a Mars mission at this scale, a country would need to shift money away from other programs. This includes defense, agriculture, transportation, social services, education, and infrastructure. No government has been willing to make such sacrifices, especially for a mission whose results will not be seen for decades. Even modern superpowers hesitate when faced with defense programs costing only a fraction of a Mars program. Asking governments to support a multi-trillion-dollar space campaign that spans generations is unrealistic under current political structures. The financial pressure intensifies when considering risk. A single failed launch, a damaged vehicle, or a faulty component can cost billions and delay the entire timeline for years. Governments must decide whether they are willing to accept this kind of risk when the political reward is small. Programs that offer concrete benefits to citizens receive faster approval. Programs that do not offer immediate benefits struggle. Mars falls into the latter category. The benefits are inspirational and scientific, but they come far too late to influence elections. During large historical engineering projects like the Apollo program, the Cold War produced political pressure that pushed the US to spend aggressively. That environment does not exist today. Without a direct geopolitical motivation, governments struggle to justify massive spending on space. Even nations that show interest in Mars often speak at conferences and publish papers, yet they avoid committing real money. They understand the scale and know that once they enter the program, they cannot leave without wasting billions. This creates hesitation that keeps programs stuck in the concept stage. Space agencies have spent decades studying the cost of Mars missions. Their conclusions remain consistent. Any safe multi-mission effort that sends humans to Mars, supports them, rotates crews, and brings them home multiple times requires funding no nation has ever committed to a civilian program. Even building the ISS pushed budgets to their limits, and the ISS is small compared to a Mars campaign. Its cost exceeded $100 billion over 2 decades. Now imagine an operation 10 or 20 times more complex. The station sits a few hundred kilometers above Earth and receives constant resupply. Mars lies millions of kilometers away and offers no chance of emergency assistance. The infrastructure needed to support astronauts has to be built entirely by humans on Earth and delivered through dozens of launches. Without hundreds of billions available, the program collapses before humans ever board the spacecraft. Private companies cannot fill this gap. Companies operate on timelines shaped by profit, investors, and corporate goals. A multi-trillion-dollar program cannot be funded privately. Even SpaceX, Blue Origin, and other major players cannot sustain costs at this level. Investors expect returns, and Mars missions do not produce financial returns. They produce prestige and scientific knowledge, but not profit. Private companies may contribute components, yet the overall cost remains a government burden. This is why no nation or alliance has committed. The numbers do not fit inside any realistic budget. The timelines do not match political cycles. The risks do not match national priorities. The cost remains too high for governments to support for 30 straight years without interruption, and a Mars program cannot survive interruptions. Even a short break in funding would cripple progress and waste billions already spent. These financial realities are not hidden from planners. They sit inside every major report on Mars exploration. Engineers know how to build the systems. The science community wants the mission. Astronauts want the mission. The barrier is not imagination or talent, it is cost. The shift toward autonomous exploration. Space agencies once treated human presence as the core of exploration because the early decades of spaceflight were built around the idea that the human eye and human judgment were the only reliable tools for discovery. That changed as robotic systems began stepping into extreme environments that humans cannot survive without heavy layers of support. And every year this shift grows larger as autonomous machines carry out tasks that would push any human crew far beyond their limits. Engineers keep improving navigation hardware and environmental sensing, and the machines going to Mars over the last decade have been built with enough independence to make steady progress across terrain that would trap a person or chew through the joints of a suit. The small helicopter that flew in the thin Martian air proved that autonomous flight is possible even in an atmosphere that barely offers lift, and it carried out dozens of flights without waiting for a pilot's command, because delays across interplanetary distances block any real-time control. The upcoming Rosalind Franklin rover adds another layer with a different drilling system and a more advanced navigation package designed to move across ground that would require humans to carry bulky protection while making slow, careful movements to avoid a fall or a pressure suit breach. These machines process terrain shapes, soil firmness, and hazard patterns far faster than a person can evaluate them, even with years of experience. And they do it without the stress that isolation or fatigue create. Artificial intelligence systems sort through rock formations, dust color variations, and chemical hints in ways that let teams back on Earth understand the ancient environment far more efficiently than any field geologist could manage while working inside a habitat or wearing a suit that restricts movement. These systems continue operating through storm seasons when visibility drops badly, and humans would be confined to shelters waiting for conditions to improve. Robotics reduce risk because nothing about these machines suffers under isolation, sleep cycle damage, or the lack of backup crews. They do not struggle with the emotional wear that long missions cause, and they do not require oxygen, radiation protection, food, or evacuation options. When engineers analyze performance data from these autonomous missions, they keep seeing the same pattern. The machines handle tasks that would drain human endurance, and they are ready to continue long after any crew would be forced to stop. The longer machines work on Mars and in deep space environments, the more obvious it becomes that they can retrieve the most important data without needing a human settlement beside them. Intelligence algorithms now sort samples, map mineral patterns, detect organic signatures, and build high-resolution models of subsurface layers. This level of analysis once required a human team on site, but advanced onboard processing narrows the data dramatically before sending it home, which means scientists receive clearer and more relevant information without large delays. With sample return missions now moving forward, robots gather material and prepare it for a transfer back to Earth, where laboratories hold the tools to run far more sensitive tests than any habitat could ever support. These missions remove the original argument that humans need to stand on the surface to collect rocks or drill for ice, because robotic arms and drilling systems already complete those tasks while avoiding dust contamination and using stable mechanical precision that does not depend on mood, fatigue, or coordination under reduced gravity. Global agencies track the cost and risk of human missions and compare them with robotic productivity, and the gap grows with every new test. Agencies continue shifting budgets because robotic missions finish more work with far smaller risk and without needing long-term logistics chains. Crewed missions require life support systems with years of redundancy, radiation shelters, psychological support, medical supply chains, and return vehicles ready for emergencies. Robotic missions need none of that. They can operate even after partial degradation, and engineers can push them far harder than they would ever push astronauts, because the worst-case scenario is the loss of a machine, not human life. This difference shapes planning cycles because administrators know that every human mission demands a level of political support that must remain stable across decades, while robotic missions can launch at smaller budgets and still deliver major findings. As a result, the scientific return no longer balances against the human risk, and agencies adjust their roadmaps to emphasize robotics while treating human missions as aspirations waiting for technology that has not reached the required stability levels. Timelines drifting away from human reach. Technology readiness levels play a major role in deciding how realistic human Mars timelines are, and each system needed for a full mission sits at a different stage. Propulsion methods that would shorten travel time exist only as concepts with no flight hardware. Shielding methods capable of holding back deep space radiation without adding tens of tons to the launch mass remain far from mature. Life support systems tested on low Earth orbit missions perform well for months, but a Mars mission demands years of reliable function without a station nearby to send spare parts. And no current system has shown that kind of endurance without constant human and ground team adjustments. There are also mass constraints that press against every plan, because each improvement in safety or comfort increases the total weight that must be launched repeatedly and assembled in orbit. The earliest feasible dates sometimes appear in agency graphics or media discussions. But when engineers update projections based on actual hardware testing, they place meaningful human missions much later than mid-century. The widening gap between ambitious timelines and engineering capability grows because the pace of robotic advancement outstrips the pace of human mission systems. Machines succeed quickly and cheaply because each test flight teaches engineers something that can be applied with minimal political risk. Human systems must pass far stricter certification, and they require hazard models that cover scenarios robotics do not face. As budgets shrink or shift toward more reliable robotic programs, the schedule for human missions drifts even further. The combination of unfinished propulsion, incomplete shielding solutions, immature life support systems, and the rising complexity of assembling large interplanetary vehicles makes the mid-century estimates appear optimistic rather than grounded. While concept art and promotional material continue appearing, the responsible engineering teams know that a human mission depends on multiple technologies reaching consistent reliability, and without those pieces in place, crews cannot be sent safely or returned securely. Robotics, already operating and improving, take the lead while human capability waits for a foundation that keeps moving farther into the future. The red planet isn't waiting, it's getting worse. For years, people imagined Mars as a quiet and still world. But the deeper the research goes, the clearer it becomes that this calm view no longer matches what long-term monitoring shows. The planet's dust cycles are growing harsher, and that development matters for any future crew more than almost any other trend. Mars has always carried dust across its surface, but early studies suggested slow seasonal patterns, predictable shifts, and long stretches of relatively clear skies. That picture has changed, as newer measurements reveal cycles that seem to build more energy than historic models expected, and that rise in energy means storms that cover wider regions, last longer, and move faster. These storms are not simple weather events. They shape surface pressure, temperature, solar power access, and visibility levels that would influence every hour of a mission. The dust grains lift easily because the atmosphere is thin, and once they rise, the lack of moisture keeps them drifting, with very little weight pulling them down. This means storms that might appear mild on paper can stretch for weeks and pull dust across entire hemispheres. When a storm begins to rise, it can knock down surface clarity faster than any crew can adjust. Visibility drops, and navigation on foot or in vehicles becomes a slow and stressful process because the horizon vanishes in a haze of suspended grains. Solar energy drops rapidly, and habitats would need backup power far more often than early mission plans predicted. Even high-efficiency panels lose output as fine dust sticks to surfaces, and this layer does not clear easily because the low pressure prevents wind from scraping it away. A crew would have to clean panels by hand or use mechanical brushes frequently, but that task itself becomes dangerous during storms because stepping outside exposes suits to abrasive particles that grind into joints and seals. The dust grain size is small enough to lodge in filters and equipment gaps, and once it gets into mechanical systems, wear increases sharply. Over time, this wear multiplies failure risks for everything from motors to airlocks. Research teams keep noticing that modern storm cycles do not settle into predictable ranges. Instead, new data reveals spikes in activity during periods that should have been calmer. Temperature swings in the lower atmosphere feed instability, and thermal contrasts at dawn and dusk trigger sudden upward gusts that lift dust in seconds. As these shifts become more common, long-term projections show that global storms may form more often than the historic average. A crew trying to work during these cycles would see reduced mobility, reduced power, and increased risk to structural materials that face abrasion day after day. Engineers want to plan missions around known windows of clear weather, but the accelerating trend suggests that safe windows may shrink, leaving crews with tighter schedules and more delays. When a planet begins shifting its climate cycles while humans are still trying to design basic habitats, it raises doubts about whether current engineering margins can handle the pressure. Dust storms on Mars cover massive distances, so when one region begins to darken, other regions feel the effects not long after. Future missions cannot rely on the surface staying stable long enough for construction or exploration objectives to move forward at a steady pace. Every storm slows activity, drains resources, and exposes systems to more stress than they were originally designed for. As these cycles intensify, the workload needed to keep systems alive also grows, and the pace of storm development matters because rapid changes give crews little time to set up shielding or retreat to safer zones. If the trend continues, Mars may present a surface where long stretches of clarity become rare, and missions that depend on steady solar power or regular outdoor activity could face conditions far harsher than anything the earliest explorers imagined. CO2 frost patterns shifting into unknown territory. While dust storms attract the most attention, the planet shows another trend that adds even more uncertainty: the shifts in CO2 frost patterns. Mars has frost cycles that involve carbon dioxide freezing directly out of the atmosphere during cold seasons, creating layers of bright ice across the poles and sometimes across mid-latitude ground. This frost expands and retreats each Martian year, and it affects pressure, surface temperature, chemical reactions, and even the strength of soil. Early models showed a stable rhythm for this frost, but newer measurements reveal that its reach and thickness do not always follow the expected pattern. These shifts matter because carbon dioxide frost shapes the entire atmospheric system. When more frost accumulates, surface pressure drops further and makes the already thin air even less supportive for any kind of outdoor activity. When less frost forms than expected, the pressure rises slightly, but temperature behavior changes because less sunlight gets reflected back into space. CO2 frost also changes the surface itself. When it builds up in unexpected places, the ground underneath experiences deeper cold than predicted, and this deep cold cracks rocks and loosens the soil. For mission planners, soil stability matters because rovers, tools, habitats, and landing pads depend on ground that does not shift too quickly. If frost cycles drift out of their old range, areas once considered safe may become unreliable. The frost also sublimates once the sun rises, and the gas released creates small pressure surges that stir dust and modify airflow patterns. These surges can feed new storms or strengthen existing ones, connecting the frost shifts to the dust cycle intensification already underway. Crews working in regions affected by these frost patterns would face unpredictable ground conditions, sudden temperature drops, and shifting pressure levels that could stress habitats and suits. Frost changes also link to long-term climate behavior. CO2 is the main component of the Martian atmosphere, and frost cycles act like a seasonal storage system. When the storage system shifts, the entire climate responds. If frost reaches deeper layers or grows in new regions, more carbon dioxide gets trapped during parts of the year, leaving the atmosphere thinner than expected. This thinness creates colder air and more extreme pressure lows that reduce lift for future aircraft, increase boil-off risk for stored propellants, and reduce the margin of safety for suits handling external pressure. If frost retreats in areas where it once dominated, more CO2 stays in the air during the warm season, raising pressure slightly, but increasing storm probability because more gas movement fuels circulation. These shifting frost cycles mean that mission planners cannot rely on old maps or old climate tables, and any crew arriving decades from now might face an atmosphere far different from the one measured earlier in the century. That uncertainty adds another layer of concern because missions need stable assumptions, and Mars is moving away from stability. If frost trends keep shifting, water ice regions may also change because CO2 frost acts as a cover that shields underlying ice from sunlight. In some areas, reduced frost may expose more ice, causing faster loss through sublimation and leaving less accessible water for crews that depend on extraction. In other areas, increased frost might bury ice more deeply under layers of carbon dioxide that complicate drilling. As frost behavior diverges from past patterns, water accessibility may decline, adding pressure to life support and construction plans. This matters because water is not just for drinking, it supports fuel production, radiation shielding, and agriculture systems. When frost shifts across decades, it creates slow but significant changes in how easy it will be to build a long-term base. And because these shifts are still unfolding, mission planners cannot rely on freeze-thaw cycles staying steady long enough to design around them. Climate models, showing rising instability for future missions. Climate models for Mars once relied on the assumption that the planet was mostly stable over short time periods, with long cycles stretching over thousands of years. But as more data is fed into newer models, patterns emerge that point toward growing instability within much shorter windows. Dust cycles are rising in strength, frost cycles are drifting, and temperature swings do not always follow historic averages. When these patterns get analyzed together, they show a planet where the next decades may not mirror the last ones, and any mission beginning long after launch planning starts may arrive on a surface different from the one engineers expected. This creates a problem because Mars missions require long preparation periods. A mission planned 2 decades ahead must rely on climate projections that remain uncertain, and if the surface environment continues shifting, those projections may lose accuracy by the time hardware arrives. Long-term atmospheric behavior already shows irregularities that affect almost every major system a crew would depend on. Temperature swings in the lower layers rise and fall in wider ranges, creating stress for thermal controllers that must keep habitats and vehicles within safe limits. Pressure dips deepen enough to strain suit integrity, because even small changes matter when the baseline is already extremely low. Wind patterns change due to shifts in frost distribution, altering dust lifting thresholds and making storms start at moments that older models would have dismissed as unlikely. These changes interfere with construction plans, mobility schedules, outdoor tasks, and even radio propagation near the surface. For missions depending on high bandwidth communication between habitats, rovers, and aerial drones, more frequent storms and altered ionospheric conditions can block signals or create interference during critical operations. When climate models show rising instability, it means engineers must build systems that can handle more stress than previously assumed. But stress margins already push against mass limits, and stronger systems mean heavier systems. A heavier habitat needs more launch mass. A sturdier suit needs more support equipment. A more durable vehicle requires more shielding and more spare parts. Mars missions already struggle with mass limits, and increasing system weight multiplies the challenge. Climate instability also means crews must carry more emergency supplies because unpredictable weather increases downtime and repair needs. This adds further mass and slows progress, making missions more expensive and more complex. Older models suggested slow changes, but updated projections point to patterns that adjust quickly enough to affect missions launched within a single career span. Future missions may face harsher surface conditions because the trend lines point toward greater energy in the atmosphere, more dust in circulation, wider temperature extremes, and frost patterns that no longer match established expectations. These shifts do not move evenly. They evolve through uneven cycles that surprise researchers by forming new regional climates that differ from older baselines. A landing zone that appears stable on maps from the 2030s may not stay that way by the 2050s. Temperature models show nights that may grow colder as frost spreads, paired with days that may warm slightly in regions losing frost cover, creating stronger gradients that feed storm development. These gradients can trigger lifting events capable of starting storms during months that once remained calmer, and those storms raise dust concentrations to levels that cut sunlight to a fraction of normal output. When a mission arrives in a climate trending towards stronger instability, the crew will face a surface environment shaped by forces still unfolding. If the dust cycles keep climbing, if the frost patterns keep shifting, if the atmosphere keeps drifting away from its earlier behavior, then each part of the mission grows harder. Power must stay stable. Equipment must stay clean. Habitat walls must stay intact. Vehicles must handle abrasive grains and shifting soil. Suits must endure long hours of exposure without wear accelerating beyond safe limits. A crew living in these conditions would carry the pressure of constant environmental stress, layered on top of all other risks. And as the climate changes further, missions planned today may run into a world that looks familiar only at a distance, but behaves very differently at ground level. Mars is not waiting for humans to arrive. It is changing on its own timeline, and the trends seen in dust activity, frost cycles, and atmospheric behavior all point toward a future where the surface becomes more demanding, not less. Each shift makes long-term planning more difficult, placing more weight on engineering margins that already sit near their limits. And while predictions evolve, the planet continues moving toward a state where human presence will require systems far tougher than the ones being designed today.